Okay, so welcome back to the lecture. Today we'll be looking at vision transformer for the first time in the series, and we'll be trying to understand the intuition behind vision transformer, how vision transformer is different from transformers that are used for text-based data. So once we have that intuition, we'll be coding one from scratch. So when I say coding, we'll write every aspect. Wherever PyTorch libraries are applicable, we will use those. And training also will be done from scratch. So at the end of today's lecture, if you are coding along with me, you will have a vision transformer built and trained by your own on one particular data set. So at the end of the lecture, that is where we are expecting to be. So first, let's look at who proposed vision transformer. So vision transformer paper idea was proposed in this paper, which was originally out in 2020, but this paper on archive or the conference ICLR was appearing on 2021. This paper 3 months ago had 65,000 citations. Now it has 76K. So I assume that few years down the line, this will become one of the, not the most highly cited paper in AI, but one of the highly cited papers in the entire history of AI. And this paper came out 3 years after Attention is All You Need paper, which was also from Google. So one thing you should note is that I remember in 2022, many people were commenting on LinkedIn and all that when OpenAI came out with ChatGPT, Google is not doing much in AI, but Google they have been doing a lot of things in AI. It's just that many of those things were not in the consumer space necessarily. Many of those things were in the research domain. And they had amazing papers, which are seminal papers. And they still do have many other papers coming out of different AI teams within Google. So this paper was titled An Image is Worth 16 by 16 Words. So what they did was they proposed the usage of transformer architecture for image classification. And in their architecture, they had very minimal changes or modifications compared to the original transformer architecture that was proposed in Attention is All You Need paper. This is a dense but well-written paper. I am premiering a 3.5-hour lecture video on reading this paper and properly dissecting the vision transformer paper. If you are interested, you can check out our YouTube. But today we are not going to be going through this paper, but what we are going to look at is how does vision transformer differ from transformers for text, which we have been exploring as part of the series. And we just want to see where the key differences are and where are the similarities. So a transformer for text works like this. You have a text input in the form of a prompt. Then this input is tokenized. Basically, sentences are divided into tokens. You can imagine when I say token, you can imagine words, but tokens can be words, subwords, etc. And then each token is converted into a vector. If it is a GPT-2 small architecture, it was of 768 dimensions. So each vector was in a 768 dimensional space. So every single sentence which we input into GPT will be converted into n number of tokens, and those tokens, each of them will be converted into 768 vectors. And to each token, we add one thing called position embedding, which we have discussed in the past. But the main difference between a text-based transformer and vision transformer comes in the part where attention is calculated. So in text-based transformer, we use something called as masked self-attention. So we have discussed the reason why this masking is done. So if we have a sentence like the cat sat on the mat, and if we are dividing a sentence into words, this consists of 1, 2, 3, 4, 5, 6. 6 tokens are there, which means there are 6 queries and 6 keys. And we construct this thing called as attention weights matrix, which we have discussed in detail in the past. But you will have 6 queries here along the row. The cat sat on the mat. And you will have 6 keys. The cat sat on the mat. And what we have discussed in the last lecture was about masked self-attention and multi-head self-attention, where in masking, we prevent current queries from paying attention to future keys. So if cat is a query that we are looking at currently, cat can only pay attention to itself and to the. Cat cannot pay attention to sat on the mat. The reason why we did this was because of the task that we were trying to accomplish. The task that GPT was trying to accomplish was next word prediction. So in next word prediction, your current query should not pay attention to keys that are yet to come, keys that are in the future. So to accomplish this, what we did was we constructed an upper triangular mask, something that looked like this, where all these elements in this attention weights matrix were 0. So this was 0, 0, 0, 0, 0. This was 0, 0, 0, 0, then 3 zeros. Only the last query, which is the query corresponding to mat, will pay attention to all the keys because there is no more query after mat. So the query mat will have 6 keys to attend to. So this is what we discussed in the last lecture. But you should also know that GPT is not the only modern architecture that utilizes transformers. There is one more architecture which is super famous called BERT. In BERT architecture, what they were trying to do was not next sentence prediction. Can you please erase the writing on the board, because on Zoom setting I cannot disable this. So my only option, if you guys draw, will be to kick out whoever is drawing. I'm sorry about that. So in BERT model, what we will have to do is, or what they were trying to do was, you will have a sentence which looks like this: the mask sat on the mask. So in BERT, which also utilized transformer architecture, they were not trying to do next word prediction, but rather they were inputting sentences, and there they were trying to predict what the value of these mask tokens were. Now, in this case, can you guys comment in the chat whether we need masked attention or not? Should we have like causal attention, which was there in the last lecture where GPT for next word prediction was used? In this case, will we use an attention with mask or will we use an attention without mask? Most of you are saying without mask. And that is correct, because in this case, you are not trying to predict the next word, but rather you are trying to take the entire context of the sentence, which means if you mask the future query, if you mask the attention between current query and future key, you won't have the full context available. And this is one reason why, if you open this paper, attention is all you need figure. Just look at this figure. Let me actually copy paste this. Now focus on this part. So this paper is not GPT paper, okay? This paper is purely attention is all you need paper. This has got nothing to do with GPT. But look at this left-hand side section and look at this right-hand side section. And tell me, where do you find the mass self-attention? Is it on the left or right? It's here in the right. There is masked multi-head attention over here. On the left, there is no masking, which means which one is GPT, which one is BERT? Is left one or is it right one? So essentially, this transformer architecture has both encoder and decoder. But in BERT model, they were just having this left-hand side part. So masked multi-head attention was not there. The input embedding was passed through attention, was passed through transformer blocks. Each transformer block had one multi-head attention without masking and one feed-forward multi-layer perceptron. And that was repeated a number of times. On the other hand, right-hand side, which is GPT-like model, it's a generative model. BERT can be converted into a generative model, but BERT is primarily not used as a generative model. It's used as a model that can learn language. So it can create very nice embeddings corresponding to a language because it has so much power to learn language. But since next word prediction is not the task in unmasked attention, BERT is not a really good next word prediction model, or rather, BERT is not a really good generative model. But GPT is that. Now, yeah, so somebody is asking, why is there skip connection? Yes, it is exactly like ResNet. So ResNet has skip connection to prevent gradient vanishing when you are performing back propagation. Exactly the reason why you have these skip connection, this. We have discussed this in detail. Now, let me ask you a question. Let's say I want to build an image, a transformer for images, okay? And what I'm going to do is, I will somehow convert image into tokens. You somehow converted a sentence into tokens. So you had cat sat on the mat, which you converted into some vectors. Each vector had 768 dimension, okay? We will do the same thing. We will take an image and we will somehow tokenize it, which we will discuss soon. Now, if my task is image classification, what kind of architecture would you rather pick? Left-hand side architecture or right-hand side architecture? Okay, many of you are saying left-hand side. Why? Why is it left-hand side type architecture? Why not right side? Want the representation, want to understand the representation of the image. The main thing is you are not trying to predict the next, image token or anything like that. You are just trying to classify. The current task that we are discussing is image classification. We are not trying to generate anything. We are not discussing about generative image models. We are trying to understand what is there in an image and try to classify into one label. Hey, this image is a cat. This is a dog. Which means if we perform masking, that is a problem because then the full context is not available. That is the reason why in vision transformer, you will not use a masked multi-head attention. You will use an unmasked multi-head attention. And that is one of the first differences that you should note. In text-based model that we have discussed so far, in BERT, they use unmasked self-attention, but in GPT, they use masked self-attention. In vision transformer, also they have transformer, but they used unmasked attention. So self-attention without masking. So this is the number one difference between image transformers for image and transformers for text that you should understand. Especially I'm talking about GPT versus vision transformer. Now there is one more difference, one more major difference, which we have to take a look at. We discussed that for next word prediction, we are using context vectors, correct? Our singular goal was to convert tokens into context vectors. Tokens had very limited information. Context vectors had much better information. And how was the context vector constructed? Context vector was constructed using this softmax of query.key transpose divided by square root of dimensionality of key multiplied by value. This was context vector matrix. And the reason why we constructed context vector was because context vectors were rich in information compared to the original input tokens, which we denoted by X. Now, tell me, if you had attention weights corresponding to, let's say, 6 queries and 6 keys, and I want to now generate the 7th token, how many context vectors do I have here, by the way? If I have a matrix like this, how many context vectors do I get as an output of this? I get 6 context vectors, correct? Because I have 6 queries, and corresponding to each query, I will have 1 context vector. Now, if I'm trying to predict the 7th token, which out of these 6 context vectors do I use? I use the last context vector. To predict the 6th context vector, we could use the 5th one, or to predict the nth token, we can use the context vector from n minus 1th query. So the information about the next token and the entire context is embedded in the last context vector. So essentially, the context vector corresponding to mat is used to predict the next token. And let's say the next token is the cat sat on the mat and something else. So then the context vector corresponding to mat will help you predict and. This is what is done in text-based transformer. In vision-based transformer, what they did was something different. They tried this. They tried an idea where an image was converted into multiple n number of tokens. Each token was a vector. Let's say 1, 2, 3, etc. up to n. They tried using one of these tokens itself to predict what the image was, but the accuracy of that was not very good. And because of that, in vision transformer, they introduced one additional token called as classification token. We can call this as classification token. So apart from the n tokens, which correspond to the image, you had one more token called as the classification token. And this classification token's context vector, so this classification token will be converted into corresponding context vector. And this context vector was used for saying whether this image is that of a cat or dog or whatever. So this is the second biggest difference that you have to notice between transformer for text and transformer for vision. So transformer for text, GPT-like model for generating the next token uses the context vector of last token for next token prediction. So this is the second difference. On the other hand, transformer in vision transformer uses context vector of 0th token. So this class token was introduced just before all the other tokens. So we can call this as class token or 0th token. It was also there in BERT. Yes. So it was the class token here was actually inspired from BERT. So BERT, what they did was if you had two sentences, you had, let's say, sentence number A and sentence number B. They started with a CLS token, and then you had T1 or TA, TB, TA1, TA2, etc. up to TAN. So you had n number of tokens corresponding to sentence A. In between, there were masked tokens. Some of them were masked. Then there was a separator token separating between two sentences, sentence A and sentence B. Then you had another set of tokens, TB1, etc. up to TBM. There are m number of tokens. And then again, a separator token. So this classification token was introduced in BERT. And this same token, this was the inspiration for classification token in vision transformer. So essentially, what vision transformer relied on was whatever is the context vector corresponding to this classification token, that context vector holds the entire information about what is there in the image. Just like how the last token holds the entire information about your sentence in a GPT, just like that, the 0th token, so now instead of last token, it's 0th token. 0th token holds the information about the entire image in vision transformer. So two differences. In vision transformer, you use classification token rather than the last token. Second thing is, unlike GPT, you don't have masking. Your self-attention is unmasked self-attention. Please note these two differences. Now, essentially, if you look at the task, okay, if you look at the GPT task, it is also sort of like a classification task. Why do I say that? Why is it a classification task in GPT-2? How could you imagine next token generation as a classification task? Basically, there is a dictionary or vocabulary in which there are a certain fixed number of tokens. So let's say there are 50K tokens, roughly 50K tokens in GPT-3. Now the goal is to say whether the input sentence, so if you have an input sentence, you will try to predict the next token, right? This next token will be one of the tokens from your dictionary consisting of 50K words. So essentially what you are trying to do is you are trying to classify whether this sentence considering all the tokens is classified into one of these 50K tokens or not. You can think of it that way, although it's not the right way to think. You can essentially think in GPT, you are trying to classify the last context vector corresponding to the last token to say which among the 50K words or which among the 50K tokens in your dictionary could be the next word. So it can be matched depending on the probability distribution. So you will get a softmax probability distribution, something that looks like this. If you add up all these probabilities, it will add up to 1. One token will have highest probability. So with highest likelihood, that token will be picked as the next token. Same thing happens in vision transformer. In vision transformer, depending on the data set that you are using to train, there are data sets with 1K image labels like ImageNet 1K. So ImageNet was a very famous data set consisting of labeled images. So there was an ImageNet small version, which was of 1K labels, and ImageNet larger version with 21K labels. So essentially, what Vision Transformer does is, Vision Transformer tries to classify the classification token into one of the 21K labels. Conversely, Text Transformer like GPT tries to classify. Classification is the wrong word. I'm fully aware of it, but I'm saying this just so that you can imagine the similarity between Vision Transformer and GPT. What GPT does, you can imagine it to be, you are classifying the final context vector of the last token into one of these 50 tokens. Because the next word, so if you have vision models are not generative. No, I did not mean that. Vision Transformer model is not generative. Vision Transformer model originally proposed in Google's paper is not a generative model. It's a model that learns about images and it can primarily perform classification. But there are other vision models which are generative, right? Just like how BERT is. BERT is not primarily a generative text model. It is a model that can really nicely understand language. Now, with these similarities and differences in our mind, let's look at the image which is directly taken from the Vision Transformer paper. So this figure, what you see is directly from the Vision Transformer paper, which very nicely explains what happens to an image when you input it. So first, you have an image, and this image is converted into non-overlapping patches of same dimension. So this image, in this example, you can see it's divided into 9 patches, which means there are 9 tokens which result from each patch. So 1, 2, etc. up to 9. Now, we perform a linear projection, which is simply a matrix multiplication. We will see how this matrix multiplication works to convert each of these 9 patches into corresponding token embedding. So this is token embedding for patch number 1. This is token embedding for patch number 2, number 3, 4, and so on. In addition to these 9 tokens, you have one more token here. And what is this token? What is this token? It's the classification token, or CLS, or class token. Now, in text-based transformer or in GPT model, just the initial token embeddings were not enough. We were adding one more thing. We were doing token embedding plus one more thing to get the input embedding. What was that? We were adding position embedding. We were adding the position information. Same thing is done here. A vector is added to the converted tokenized patches corresponding to the position embedding vector. Now, these vectors were learnable vectors. So the value inside these vectors were not fixed. But the way it works is, if each patch, let's say your patch is of size 16 by 16, this might be converted to a 768 dimensional vector. To this vector, your position embedding will be added, which is also of 768 dimension, but the values inside this vector will be a learnable parameter. In Vision Transformer paper, if you read the paper, they have tried both. They have tried fixed position embedding, meaning you can easily construct a position embedding considering the fact that 0th token is at the top left corner, last token is at the bottom right corner. So you can nicely try to construct some vector which captures the idea that which captures the relative distance or relative position between these patches. You can definitely do that. So they have tried both. In the paper, they tried fixed position embedding without learnable parameters and learnable position embedding. and both were giving similar accuracy. And in the main paper, they used learnable position embedding. Now, once you have learnable position embedding, you also need to add learnable position embedding, by the way, to your classification token. So this is the class token, CLS token or CLASS token. To that, you add zeroth position learnable embedding. So now you have position embedding plus tokenized patches, plus you also have the same thing for CLS token. Now you have the entire tokens available. Then what you do is you pass these tokens to your transformer encoder. Class comes from the label of labeled images. No, this class has nothing to do with label at the moment. At the moment, it is just an extra token that is added, whose value during the backpropagation will be changing. I'll tell you how it changes. Right now, don't think about that versus labels. This classification token is simply zero token. That's it. And that token's context vector will be used for classification. Then transformer encoder looks exactly like the left-hand side, or almost exactly like the left-hand side of the attention is all unit paper. So this left-hand side was BERT-like model or vision transformer-like model. And LX means this block, transformer block, will repeat L number of times. The value of L can be 12, 24, etc. In the paper, they have tried 3 models, vision transformer base, large and huge or something like that. 3 models, if I remember correctly, they have tried. The only difference is the location where this layer normalization happens. So in the attention is all unit paper, this layer normalization was happening after multi-head attention. This layer normalization was happening after feed-forward neural network. So this was called post-layer normalization. Here, on the other hand, they tried pre-layer normalization. So this is before multi-head attention, and this is before multi-head attention, multi-layer perceptron. So this was the only difference. Now, if you ask me what difference this brings in accuracy, I have no idea. If I were the one who was building vision transformer, I will try both. I will see which one works better. That is the only way. Otherwise, it's very difficult to say which layer normalization works better. But you should note that this is the primary difference. So this is now the transformer encoder used in vision transformer. And this left-hand side is the encoder proposed in attention is all you need paper. This was repeating n number of times. So nx means the transformer block was repeating n number of times in series. Here it was repeating same, just they used a different variable name. That's it. L number of times in series. But you see that these two things are almost exactly the same, except for the position. Pre-layer normalization in this case. In this case, it's post-layer normalization because it's done after the MLP and after MHA. Now, the images, the way it is tokenized, it's converted into patches is not based on number of patches, it's based on patch size. So here, the title of the paper is an image is worth 16 by 16 words. So here they use patches of size 16 by 16. What that means is if you had an image whose dimension was 64 by 64, or let's say your patch size is P by P, and image height is H, and width is W, you will have H by P patches along the height, and you will have H by W patches along the width. So total number of patches would be, sorry, my bad. W by P patches along the width. And total number of patches would be HW divided by P square. Number of patches, where P is the patch size, H is the height, and W is the image width. Now, if image size is like square, and if we call that using IMG size as the variable, you can simply say IMG size square divided by P square. This will be the total number of patches. And if I call N equal to IMG size divided by P the whole square, what is the total number of tokens that go into my transformer encoder in vision transformer? Number of tokens that let's say multi-head attention should expect in the vision transformer equal to. So my question is, this is the number of, this N is number of patches. Isn't that correct? Total number of patches. how many tokens will enter the multi-head attention, MHA? It will be n plus 1. So it will be 1 plus image size divided by patch size, the whole square. Why? This one is for classification token. These n number of tokens correspond to the images. So that many tokens will be entering into my transformer encoder. Okay. Now, after transformer encoder, here, based on what I have mentioned, what comes here? What is passed into this MLP head? I'll tell what this MLP head is, but tell me what goes here. From transformer encoder, what goes here? What goes here is, we can call it as, so if input we call as X. So X0, let's say it is CLS tokens input. Let's say this is X1, etc. up to X9. And let's say after each transformer block, X will become Z. So let's say after first block, it's X0, Z01. After first block, first token will become Z11. Like that, ninth token will become Z91. Like that, I have L layers, which means Z0L, Z1L, etc. up to Z9L. So this Z is the context vector corresponding to Z0 is the context vector corresponding to 0th token after Lth transformer layer. So Zij is the context vector of ith token after jth transformer block. And I runs from 0 to 0 is the classification token, and it runs from I runs from 0 to HW by P square. And J runs from 1 to L. You have L transformer blocks in series. You have n plus 1 number of tokens. The 0 token you can call as 0, and then the last token will be HW by P square. H is the height, W is the width, P is the patch size. So n equal to, it is the same. So it is, see, if your image size is 64 by 64, and if patch size is 16 by 16, right? This is 16 by 16. This patch can be fit 4 times along the row and 4 times along the height, right? Which means I can have H by P number of patches along the height multiplied by H by P patches, W by P patches along the width, which is HW by P, which is image size. Image size is either height or width, the whole square divided by P. If it's a square image, if it's not a square image, H need not be equal to W always. It just needs to be divisible by the patch size. So what goes into my MLP head will be Z0. What will go into my MLP? Z0L. This is the context vector corresponding to 0th token, which is the classification token, after the Lth transformer layer. So this is what goes into my multi-layer perceptron head. And this will be a 768 dimensional vector. Now this vector is passed into MLP head, which will simply look something like this. I can simply say I have 768 that multiplied by 1 layer. And then let's say my output, in the output, I have 21K classes. If my data set belongs to ImageNet 21K data set, then I'll have 21K nodes here. So the dimensionality here will be 21K multiplied by 1. And I can have fully connected connections. Every node is connected to every other node. So how does this transformation happen? How do you go from 768 by 1 vector to 21,000 by 1 vector. What do you use for this? You use a matrix. Let me just stop sharing and I'll reshare. Yeah, you will use a matrix of dimension 21,000 by 768. So 21,000 by 768 matrix. You multiply this with 768 by 1 vector to get 21,000 by 1 vector. So you can use this to, now this matrix will be again learnable parameters. So that matrix will form the weights here, W11, W12, etc. up to W1 21,000, then W21, 22, W2 21,000, W31, 32 like that. So basically these weights are the values inside this W matrix. So essentially W multiplied by Z0L will give us our Y. And we can take softmax on this Y to get probability distribution. Hidden layers, I don't think it's needed. Hidden layers are there in the multi-layer perceptron over here. But in the MLP classification head, it's just a classification header. But here there is a hidden layer. All right. So this is essentially what a vision transformer is doing. Now we have to do coding, right? Now let's see if we were coding, what all things should we focus? Let's write down. First, we should have data set. So MLP head is different from MLP in transformer layer. Exactly, it is different. Here, see, MLP is simply a neural network, feed forward neural network. So it will not have any convolution operation or anything like that. So MLP head is just transformation or linear projection of your, in fact, I won't say linear because it has non-linearity. It's a projection from your classification token after the transformer encoder into whatever is your number of classes. So if your number of classes is 10, in our case, in fact, we will be having 10 classes, not 21K classes. You are projecting your 768 dimensional vector into 21K or into 10 or whatever your number of classes are. But this multi-layer perceptron has a different purpose. This multi-layer perceptron is used to enhance or enrich the context vectors themselves. So in this MLP, what was done was, let's say your context vector is, let's say in Lth layer, your context vector Z looks like Zi or Kth layer, Zik with 768 dimensions. So you will have 768 dimensional, these many nodes. This will be projected into a higher dimensional space, 768 by 4, typically a 4x dimensional space. And then you will project it down again into 768 dimensional space. So this projection into a higher dimensional space and back into its original dimension, this can enrich the features because in this space, you have 4 times more dimensions and all these are learnable parameters. All these weights are learnable parameters. So this is the opposite of like variational autoencoder. I mean, autoencoder. In autoencoder, you encode into a lower dimensional space and then you try to decode. Here you are trying to project it into a higher dimensional space in the hope that your context vector will become much richer. And in fact, there was an assignment which I had posted, and there is also a video which is coming out today at 2 p.m. on our channel, where you will see that this MLP carries almost 2/3 of your total number of parameters. Total number of parameter means if you have 175 billion parameters in your GPT-3, for example, 2/3 of that belongs to your all multi-layer perceptrons in the transformer blocks added together. Only remaining 1/3 of the parameters are found in multi-head attentions. And very, very small fraction, like 2% is only found in the rest of the architecture. So here, in GPT, basically, 1/3 was found here, GPT-3. 2/3 of the parameters of 175 billion is found here, not in just one, in all the 96. So in GPT-3, they had 96 layers. So all the 96 combined, MLP will take up almost 2/3, MHA will take up almost 1/3, remaining will take up 2% roughly. So multi-layer perceptron carries a very big role. Okay, now let's think about encoding this. What all do we need? First, we need data set. Second is we need to have some way to tokenize the data set. Okay, there's a question, why can't we stack the context vectors and send to MLP just like normal transformers like sentiment analysis? For stack up, you mean concatenating the vectors from different multiple heads? That's not what you're asking, right? You're asking about all the tokens, right? All the context vectors somehow either added or concatenated. Is that what you're asking, Sandeep? I don't think in GPT anyways, they were not doing that. They were doing that in multiple heads of the attention head. In inside one transformer block, you will have, let's say 96 attention heads. Each attention head will take care of 1 by 96 dimensionality, whatever should be the output dimension, and then you will concatenate. But at the end, you are not concatenating all the context vectors. You are simply using the last context vector for next word prediction. So same thing is being done here. So in vision transformer, they explicitly mention at one place that they wanted to introduce minimum change to the already popular transformer architecture, which was introduced in Attention is All You Need paper. But I mean, yeah, I wouldn't be against trying, just like don't use classification token at all. Try if the context vectors corresponding to the rest of the tokens. If you have n+1 tokens, don't use classification token. Don't introduce it in the first place. Just use the n token somehow and see if you are able to represent the image to get good classification accuracy. It is something worth trying. In the paper, they have tried it, but their accuracy was not good. In an image 640 by 640, what do you mean by token? Yeah, so in 640 by 640 image, the total number of patches will be 640 divided by 16 multiplied by or square of this, which is what, 40 square, right? So 1600. So each patch will become one token. So each 1 by 40th of the or 16 pixel patch in that big image, this will become one token, this will become one token, this will become one token, and so on. So that is what I mean by tokenization. Patch will become vector. Patch is just a two-dimensional image. Vector is just a multi-dimensional numbers. So yeah, so we need data set. Next, we need to convert data set or images into patches. So we need some sort of patch embedding algorithm. Then we need a transformer encoder. So this is the second part of this. This is the part 1 of the vision transformer. This is part 2 of the vision transformer. Fourth is we need MLP classification head, so or MLP head. This is the part 3 of the vision transformer. Then perhaps we can have one class written in Python where we can just say have one vision transformer class which combines part 1 plus 2 plus 3. Part 1, 2, 3 we combine. Then we need a training loop, or before that we have to define like device equal to CUDA optimizer device. We have to define let's say epochs and bunch of things. So that I forgot to mention. Let's say variables, bunch of variables we have to define. Then we can also have a validation data set, and we can see how much is the validation accuracy. And then finally, we can have some sample test on some sample images. So display some images from our data set and see what the vision transformer is predicting for classification. So sample classification prediction. How to do regularization in transformer? Layer normalization is the particular technique. So layer normalization is one, but in transformer, they also use dropout right after the, okay, meeting room. Yeah, so they also use dropout right after the multi-head attention. They also use dropout. I think they use it optionally after multi-layer perceptron also in the transformer block. But the other technique is layer normalization, sample classification, prediction. So if we can do these many items in today's lecture, we can say at the end we have built and trained the vision transformer architecture, right? So that is exactly what we are going to do now. So what I suggest is I don't have any single line of code written yet. I'm starting from this empty Google Colab notebook. So you can also open Google Colab and you can write the code along with me. Can you see my Colab first of all? Can you see the Colab notebook? All right. So now I'll tell you what may happen. While writing the code, maybe some mistakes might happen on your end, and there are 100+ people in this call, and it's impossible for me to look at everybody's, let's say, syntax issue or some error that might have happened. Ideally, if you are coding exactly the same as what I'm doing, things should work, but I'm foreseeing some errors to happen to people. In that case, just post the error and you guys please try to help out yourself. I'll try to maximum help, but I can foresee that some issues can happen. That's the first thing. Second thing is, I don't think you need GPU or anything. The code is reasonably fast. We will be working on the MNIST dataset, which is one of the simplest datasets to work on. So MNIST is simply this handwritten digit classification. So it's like a 10-class classification dataset. And if you don't have Colab Pro, you can still have, I think, one of these T4 GPU, I think you will have. I have all of them because I have Colab Pro. But in your case, I think you should have CPU or T4 GPU. Just check that. Whichever is available, you can use that. But in either case, even if you just run with CPU, I don't see it will take too much time for you. It should be fast. So now let's start writing the code. We will start from the very basic. Let me also take some notes so that I'm not making random silly mistakes. The first thing we can do is import some packages which we will need. Not all of them. Some of them we'll import now. Some of them we'll import on the go. All right. So we will need torch, PyTorch. Then we will need data loader, import torch. Then let me increase my font size. I hope this is better. Import torch dot utilities utils.data as data loader. Let me just have these two things for now. Remaining, I know that there are bunch of other libraries that we require, like nn.module. Maybe I can import that also. Import torch.nn as nn. So all these three are basically from PyTorch. Okay, so just have this ready and run the code. I will just switch to maybe TPU. Then the next thing is, let us get the data set. So download data set, basically MNIST data set. And this can be done from Python image library or PIL, PIL. So Python image library has a bunch of data sets. It's not just MNIST, there is fashion MNIST and many other. Yeah, training and loss forward and back. Yeah, it will all fit over in the training loop. So first of all, I'll tell you where we don't have to do some things from scratch, which is the whole reason why we are using NN. But I'll also tell you the training loop part. Okay, so we have these three libraries, but we will need a few more libraries. We'll figure out on the go. Now we have to download some data set, which is MNIST. So train underscore data set. So this is the training data set. And this we will download from Torch Vision, which means we'll have to import Torch Vision also. So import Torch Vision. So PyTorch for computer vision. Just run this. So these four, please ensure that you have these four. Torch Vision dot datasets dot MNIST. So we are getting MNIST dataset from the datasets in Torch Vision. And we want the dataset to be stored somewhere. We can say root equal to dot/data. So in the folder over here, it will create a data folder in which the MNIST dataset will be downloaded. This can be pretty much anything, but just give dot/data or something like that. Then this is the training dataset, which means I have to say train equal to true. And that's it. Similarly, copy paste this. Yes, you can use any dataset, your own dataset. It's fine. MNIST, the reason why I choose is I know that MNIST dataset can be trained in a reasonable amount of time. So you can see, you'll be happy to at the end of the day see a good accuracy, right? At least by the end of the lecture. That's the only reason why I choose MNIST, but otherwise you can choose any dataset. Next is validation dataset, torch.datasets.mnist. Everything is the same, train equal to false, which means this is not a training dataset. So this is the dataset download part. Let me put it here. Now there is one issue here. This dataset is taken from Python image library or Pillow, but we need to convert this dataset into tensor format because PyTorch or neural networks defined using PyTorch will expect tensor format input, which means we have to define certain transformation here. So transformation or transform equal to, it's expecting something. So let's define what this transformation is like. So data transformation for converting PIL to tensor format. So define the transformation earlier. So data transformation, you can define whatever variable you want here. Variable name is not an issue. Here it should be transforms dot compose of transforms dot to tensor. So we are defining the transformation from PIL to tensor format. And here we will have to also import torch vision dot transforms as transforms. So from this transforms is where we are calling the to tensor function. So just define this data transformation. Transforms is not defined. It's because I have not run this block of code. So now see, I have these 5 things, okay? Just make sure you also, everything is from PyTorch or Torch Vision. Then I have to just pass this transformation, data underscore transformation, we pass here. So transform equal to data underscore transformation. Do that for both validation data and training data. So train dataset equal to torchvision.datasets.mnist. Then root, we define the folder path. Train equal to true for train data, train equal to false for validation data. Transformation is the transformation that we have defined here, which is converting the PIL data to tensor format. And then you run the code. Download equal to true. Yes, we need to mention that also. Download equal to true. So mention download equal to true for both training and validation data. All right. So hopefully so far it should work for you. It's very basic code. Now we need to do one thing. In neural network training, we usually use dataset in batches. We don't train one image at a time. We train one batch at a time, which means we have to create batches using training dataset and validation dataset. So create batches for neural network training. This is where we use the data loader, which we have defined here. So now we can say train underscore loader equal to something, val underscore loader equal to something. Now what will this be? Data loader dot, from this we call the function called data loader. So data loader is imported here. So torch.utilities.data is imported as data loader. From that, we are calling this data loader function. And into this, we pass, for train loader, we pass the training data set. And then since we are creating batches, obviously we have to mention the batch size equal to, let's say, 64 or something. And we have to say shuffle equal to true to shuffle the training data. But for validation data, we don't have to shuffle it because we just need to see what's the validation accuracy. So this can be kept true or false for validation data set, doesn't matter. Now, one more thing that will be nice is instead of this batch size being a fixed thing like 64, it'll be great if we can have some variables defined. So now let's see what all variables do we need. So I can maybe define variables up here. Variables that I need. Yes, val loader should contain val dataset. Yes, thank you. So variables I need, let's define what all variables we need. Firstly, we have image size. And we know that this image size, we don't have to calculate since we are using MNIST dataset. We know that image size is 28 by 28 or something, right? That we can just define. But if we are changing the dataset, it's better to use it as a variable, but here it's okay. So image size is 28, which means a good patch size to choose will be a number that perfectly divides the image size. So patch size we can keep as 7, which means along the height, there will be 7 patches. Along the width, there will be 7 patches. So totally there will be 16 patches. But if we keep patch size as 14, there will be 4 patches per image. And then we can say number of patches equal to image size divided by patch size. And this we have to do 2 times. So this is along the width and this is along the height. Or we can simply say this raised to 2. Raised to 2 is 2 times multiplied symbol, raised to 2. But this will have one problem. Can anyone tell me what problem this might have? This line might have a small issue. Yes, floating point. So what we can do is either we can convert to an integer or we can just use this floor operation. So floor operation, what it does is if the image size was 30 and patch size was 7, 30 is not perfectly divisible by 7, there is a remainder. But float operation, this floor operation will pick the lowest integer, the integer just before. So we can do this. And then if we print number of patches, it should be 16. Otherwise, it will be 16.0. If this is not there, it will be 16.0. 16.0 is not the number of patches. It has to be an integer. So let's use this. No, we are not losing information here because patch size and image size, this number is perfectly divisible. We have picked the patch size such that it's perfectly dividing image size. Okay, now what we need is dimensionality of the token. So token dimensionality, let's say it is something like 32. So each token will be 32. Then we need number of heads, which is number of heads in the multi-head attention. Let's say it is 4. So this is what? This is L, right? The parameter L. No. So this is not L. Number of heads is a number of heads in each attention head. Attention heads is the transformer blocks is the value of L. So this will be, let's say this also is 2. So this is L. This one does not have a variable name yet, but images are not color. This one is black and white, just grayscale image. Shouldn't the token dimension be 10? No, token dimension is the dimensionality of the vector, which we said has to be 768. Number of tokens is 10, or number of patches is this, but token dimension should not be 10. Token dimension can be anything. Number of tokens is also not 10, that was my bad. Number of tokens is whatever is your total number of patches plus 1. Token dimension is whatever should be the vector that corresponds to each token, the dimensionality of the vector. It can be anything. It need not be equal to the number of classes. So token dimension is equal to, let's say 32 for now. Number of classes is 10. Num classes equal to 10. Yes, number of heads here, I think it should be, ideally it's better if it's divisible. 32 and 4 are divisible. So each attention head will take care of 8 dimensions. And if you concatenate 8 4 times, you will get back 32. But if this was 30 and this was 4, I think it will cause an issue. So, or if this is 32 and this is 5, I think it causes an issue. So this 32 should be, whatever this is, should be divisible by this. Number of head y0 is the transformer blocks number. So transformer blocks is the number of times. Let me go back to my board. Transformer block is different from number of attention heads. Transformer block is how many times does this thing repeat? How many times does this whole thing repeat in my architecture? Here it repeats L number of times. So the value of L is whatever is the number of transformer blocks. But here in multi-head attention, you will have multiple attention heads here. That is different. So multiple in GPT, they had 96 attention heads here itself. 96 attention heads here in each transformer block. And like that, these transformer blocks themselves were repeating in series 96 times. And these attention heads were operating in parallel. Like that, you have 96 attention heads in block number 1, in block number 2, in block number 96. So this is the number of blocks. This is the number of heads. And in our code, the variable name is number of heads is equal to 4, which means this is 4. This guy, the number of heads parallel here. Number of transformer blocks is also 4, which means the number of times this whole gray color block will repeat in series will be also 4. Now, how does multi-head attention process your input? Your input comes, and let's say input is having 16 dimensions. Output that comes out of multi-head attention is also 16 dimension. And let's say you have 4 attention heads in your multi-head attention. Okay. Let's say there are 4 attention heads. The final 16 that you get here is the result of concatenation of the output from 4 attention heads, which means each attention head was taking care of a 4-dimensional query key vector. This was taking care of a 4-dimensional query key vector. This was taking care of a 4-dimensional. And how do you get that 4? It is 16 divided by your number of attention heads. So if your attention heads was 5, it would have caused an issue because 16 and 5, you cannot divide 16 by 5 perfectly. So you cannot define how many dimensions does each attention head take care of. So each attention head, whatever output you get from each attention head. So let's say this is 16 and you have attention head number 1. This is query, key, value. And like that, let's say there are 4 attention heads. Then what comes out of here, the query vector is 4-dimensional. This is 4-dimensional. This is 4-dimensional. Query, so this is QKV, QKV, QKV. So these are all 4-dimensional. 4-dimensional, 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 4, 4, 4, 4, 4, 4. And then this query and key, you take dot product to produce attention weights matrix eventually, which will be 4 by 4. And then you multiply that with the value vector to produce your context vector matrix. Okay, here you can't say it's 4 by 4 because I don't know how many tokens are there. But attention weights matrix and then the context vector. Context vector will be 4-dimensional. Here also it will be 4-dimensional. Here also it will be 4-dimensional. And this also will be 4-dimensional. And then after the 4 attention heads in multi-head attention, you concatenate these such that 4-dimensional, 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 4-dimensional. This will be back into 16 dimensions. So this is how it goes through. 16-dimensional input comes into and goes into 4 attention heads in your multi-head attention. So now this is your MHA with 4 heads. And when it comes out of MHA, you concatenate it to get back 16-dimensional vector. This is why, so this 4 equal to, the way you get 4 is, so MHA dimensionality is equal to dimensionality at the output, D out, which is 16, divided by number of heads. So MHA dimensionality in this case will be 16 divided by 4. If there were 2 attention heads, it would have been 16 divided by 2. Each attention head would take care of 8 dimensions each. So that is the reason why here number of heads is 4 and token dimension is 32, which means each head will take care of 8-dimensional query. The query key space is 8-dimensional. Okay, number of classes is 10. Why do I use D out? You use D in. So the reason why I explicitly said D out is sometimes D out can be different from D in also, although in GPT, D out is equal to D in. So for the case of GPT, instead of saying D out, I can say D in. But you can technically have D out to be different from that of D in also. That's the so the right thing to say is D out, because after the concatenation is where you get D out. So technically, D out divided by number of heads is the dimensionality of each attention head. It need not be exactly same as D in, although in GPT it is exactly same as D in, but it need not be that way. Okay. So now, how is L combined? L is not combined. L is just put in series. We do not combine the L dimensional. Oh, let me connect my charger. We do not combine the inputs from each of the L transformer blocks into one thing. That we do not do. All right. What else is there? We have to have number of transformer blocks. Yes, MLP hidden dimension. So this hidden dimension is the number of dimensions of the NLP in where? In this one. In this MLP here. And that we can say, let's say it is, let's keep it bigger than the token dimension. In GPT, it is 4 times token dimension. So it is usually 4x token dimension. But here I don't care about that. Maybe I can keep it as 64 and then we can play with this. Then maybe we can say learning rate during my backpropagation, 3 times 10 to the power of -4 or something. This we can play with. Again, it's a hyperparameter. Number of epochs equal to, let's say, 5. I don't think I'm missing any other parameter. I think that's pretty much it. Number of, oh yeah, one more thing is number of channels. So if it's an RGB image, number of channels will be 3. This is a color image. This is a black and white image. So, or rather grayscale image, number of channels equal to 1. So these are my variables. If I need any other variable, I'll define it later. So this is the image size 28 by 28, number of channels equal to 1. It's because it's a black and white image. Patch size is 7 by 7, which is the dimension of the each patch of the image. Number of patches will be image height divided by patch size multiplied by image. Oh yes, batch size. Very good. Excellent. Batch size equal to 64. 64 or 32, whatever, I can pick anything. But here, then I will use this variable instead of 64. All right. So I think these are the variables that I need. I don't need any more. If we need any more, we'll figure it out. So just define these variables before you run the train loader and val loader. And here, just pass the batch size variable rather than passing the, number 64. Okay. Now we need to define 3 things. So first is part 1 of vision transformer, which is patch embedding. Then second thing is part 2 of vision transformer, which is transformer encoder. And next, part 3 of VIT will be MLP head, classification head, MLP classification head. And then I can say part 1, 2, 3 combined. So these are now the 4 things that we have to write. And after that, we can run the training loop. Should the batch size be multiple of total number of tokens per patches from each image, or that doesn't matter? So batch size is nothing but, so batch is not related to tokens. Batch is related to number of images. I'll ask you one question. Let me come to that. Does query for CLS token attend to all token keys patches? Yes, it does, because it's not a masked attention. Query from every token, including CLS token, attend to every patches, including CLS tokens and all the other patches. Import needs to be corrected from torch.utils.data import. So here what I'm doing is I'm calling this import torch.utils.data as data loader, and from here I'm calling data loader dot data loader, or otherwise I could have just written like this, torch.utils.data dot data loader. So either way it works. All right. Now let's write patch embedding. So this will be a class. Now here, what token dimension means here when we have image, it's about pixel. No, it's not at all about pixel. See, if we were treating each pixel as a dimension, now imagine if you have a high resolution image, your number of dimensions will be so high. Here, token dimensionality is what do you convert your patches into? What dimensional vector do you convert your patches into? Is it 1-dimensional vector? Is it 2? Is it 3? Is it 768? You essentially are converting into vector. Now, what should that vector's dimension be? It is not directly related to input image embedding, input image pixels. So now here we are going to write 4 classes actually. Part 1 will be a class, part 2 will be a class, part 3 is a class, and part 1, 2, 3 combined will be another class. So this class we call as patch embedding. Now there are a few things which I want you to note here. Firstly, in patch embedding, we will be passing something called nn.module. So nn.module is very important. So there are certain properties for classes. Classes can inherit properties from its parent class. Classes can pass properties to some other class. So here, essentially what we are doing is, if you remember, import torch.nn as nn. So we are inheriting certain properties from PyTorch's nn for neural network. So this, if we pass nn.module into this class, then whatever neural network we define inside this class will be defined according to PyTorch compatible format. So whenever, and you will see this almost always, whenever you are writing or building neural networks from scratch using PyTorch, to most of the classes, you will be passing nn.module, or the properties which are there already defined in PyTorch's nn, you are importing it here. So class patch embedding, into that you are passing nn.module. Now the first thing that we have to do for every class is define init. So this is 2 underscores, okay? So underscore init underscore self. And I'll tell you what exactly we are doing here. So first thing, in Python class, what happens is, the reason why you are defining classes so that you can later instantiate the class by creating objects. And whenever you create an object, that is when you will initialize the functions that are defined in the class. So when you are defining a class, this thing will you will always again and again you will come across this. The more you use this, the more the intuition will be. But basically, whenever you are creating a class, whenever you are creating an object corresponding to a class, it is called, or it is in Python, it is referred to as, that object is referred to as self. And then this self is passed into this init constructor. And this is one of the default things which you will come across in almost all classes. You can write Python function also, but the easiest way to do to take properties from nn.module is to define it as classes, because there is now a parent class, now there is a child class. So now I'll show you how to inherit some parent class properties. So super dot underscore underscore init underscore underscore then functional bracket. Now what this tells is, so this init belongs to which class? Patch embedding class. But there is one init in nn.module also. So this super tells that you are now initiating, or you are now calling the init constructor from your parent class, which is whatever you are inheriting from nn.module. So two things, and this in all the 4 classes that we are writing today, these 2 lines will come again and again. Okay, so please note this. So first one is defining the init constructor for our current class, which is patch embedding class. Second thing is we are asking it to look at the parent class, and the parent class is nn. And in that there would be another init constructor defined by whoever wrote PyTorch, whoever wrote nn. And then this super is saying you initiate the init constructor from that class. Okay, super, then functional bracket dot underscore underscore init underscore underscore. All right. Now we say self dot patch underscore embed. So this is now the defining the action of patch embedding. Now let's see what exactly do we need to do in patch embedding. Let me go back to my whiteboard. So I have an image of size 28 by 28. And like this, I have a batch of how many images? 64 images. So my batch, not patch, batch B. So I have batch size of 64. I have number of channels per image of 1. I have image size of 28 by 28. So this is how my dimensionality will look like. So this is batch underscore size. This is number of channels in the image. This is width of the image, height of the image. Now, what do I want this batch to become? Batch size should not change, because if I have 64 images in one batch, that batch size should remain the same, correct? But what should each of these images, what should it become? Ultimately, this whole thing, each image should become 16 patches. Each image should become 16 patches. Why? Because my patch size is 7. If patch size is 7, I have a rectangle like this here, 14, 21, 28, and like that along the width, along the height also. So each image should become 16 patches, and each patch should have a dimensionality of what? 32, correct? That is what we have defined here. Token dim is 32. So I want my input of dimension 64, 1, 28, 28. After my patch embedding, this is what I want it to become. So now this is the batch size. See, think about this. Before I add my classification token, what do I have? Before I add my classification token, I simply have 16 patches, correct? And classification token is added to 16 patches whose vector dimensionality is 32. 32 can be 128, 768, whatever it is. But here we have defined 32. So I have 64 images in a batch. So this is batch size. I have 16 patches in an image. So this is number of patches, num patches. Each patch becomes a vector. So this is embedding dimension or input dimension. Now this is what I want to become. Number of channels, it doesn't matter whether we are inputting RGB image or color image. At the end of the day, whether the number of channels are 3 or 1, it should become this, right? If my batch size was 1, then I will simply have one image in my batch. Each image will become 16 patches. And then each patch will become 32-dimensional vector. Now let's see how to make this happen. My image has one channel of dimension 28 by 28. Now, first, what I can do is, let's say, now we know that this is not a convolutional neural network. This is vision transformer. And one of the biggest value propositions of vision transformer itself is that it does not use convolution operation, right? But we can very cleverly use one convolution operation, which is essentially a matrix multiplication, to convert your image into patches. Now, let's say I had a convolution operation whose kernel size is this much, is 7 by 7, whose kernel size is 7, whose stride is 7. Okay, so let's say I had a conv2D operation whose input number of channels is 1, whose output number of channels is 32, whose kernel size is 7, whose stride is 7. I will write these numbers. So this is input channels. This is output channels. This is kernel size. And this is stride. Okay. Let me make you understand how does RGB image get converted to, in any convolution operation, how does an RGB image get converted to an output? So let's say I have an RGB image. Yes, currently we are assuming we don't have RGB channel, but let's keep it as an RGB image for once. Let's say this is an RGB image. So number of channels is equal to 3. Dimensionality is 28 by 28, correct? And let's say I have one filter, one convolution filter, whose dimension is 7 by 7, whose stride, there is no padding, I'm not adding any padding, stride is equal to 7. Okay. What will be the dimensionality at the output? Let's say this is my input. This is my convolution operation. Now I have to have an output. What will be my output? So stride is by how much will your this thing jump. So stride looks like this. This is by how much will your convolution filter jump in each convolution operation. First it will be here, then it will be here, then it will be here, then it will be here, like that. So can you tell me what will be the dimensionality of my output? Spatial dimension, what would that be? Spatial dimension will be 4 by 4. There is no doubt about it, right? Because you have a 7 by 7 convolution kernel with stride 4 acting on a 28 by 28, but spatial dimension will be 4 by 4. But my question is not about spatial dimension. That is very easy. What should be the Z stack dimension? What should be the number, the number of stacks? So this is 4 by 4. Will the number of stacks be 3, or will it be 1? My question is this. Spatial dimensionality of the output is 4 by 4. Anybody can see that. What should be the Z stack dimensionality? Will it be 3 or 1? For those of you who said 1, why is it 1? So the way it works is your number of channels. So one thing I have not shown here is your number of channels here in your convolution filter will be 3. And the way it works is, let me just combine this. First, it will operate here across all the 3 layers. Then it will operate here across all the 3 layers, all the 3 layers, all the 3 layers, like that, to produce 1 channel output. It does not produce 3 channel output, it produces 1 channel output. So this convolution filter will have 3 channels, but the number of filters, so channels in the convolution filter, in the convolution is equal to 3, but number of filters equal to 1. And the number of channels at the output should be equal to number of filters. So num channels or output num channels is equal to number of filters. Here you have only 1 filter with 3 channels, which means the output will be 1 channel output. If you want 3 channel output, you will have 3 filters like this. Filter number 1 taking care of first channel at the output, filter number 2, filter number 3. If we have something like this, then I will have 3 channel output. Then how does it work? This filter will take care of the first channel. This filter will take care of second channel. This filter will take care of third channel. Then the 3 filter values are combined by weighted addition. Just like how in convolution in spatial 2-dimensional, it is like a weighted addition, right? Same thing. Along the Z also, it is added. It's not average. Average also can be done, I guess, but usually it is addition is done. So this is how, if you had an RGB image. So now think about this. If I had just 1 filter, okay. So now let's come back to this. How 3 channels are converted to single channel. It's just like this: 1, 2, 3, 4. Let's say this is my image. This is my second channel, third channel. Okay. Now let's say my filter is looking like this. Filter should have 3 channels. And let's say the value here is 1. Then the output corresponding to first one will be 1 times 1 plus 1 times 1 plus 1 times 1. So first output will be 3. Second output will be 2 times 1 plus 2 times 1 plus 2 times 1 will be 2 times 3, 6. So the final output will be 3, 6, then what? 3 times 3, 9, 12. But now this output has only 1 channel. What if I needed 3 channels? Then I will have 3 filters like this. And now let's say my filter number 2 has values 2, 2, 2. Then my channel number 2 in my output will be 6, 12, 18, 24. And then let's say this value is -1, -1, -1 in the third filter. So now this is filter number 1 with 3 channels, filter number 2 with 3 channels, filter number 3 with 3 channels. This is input number 1 with 3 channels. But now this is the output which has 3 channels. And filter values are learnable parameters, exactly. Now these values will be -3, -6, -9, -12. So this is how, see, now look at this. This was an RGB image. And this RGB image can be converted to a 3-channel output. It can be converted to 1-channel output. It can be converted to any number of channels. It depends on how many filters you have. If you have only 1 filter, you will have 1 channel output. If you have n filters, you will have n channel output. The spatial dimension of each channel will depend on the filter size and stride. Okay. Now with this knowledge, let's come back to our goal. Our goal was this. We had 28 by 28 filter. Not filter, image. And just 1 channel. Now, I have 64 images in my batch. So let's forget about the batch for a moment. Let's assume that my batch size is 1. What I want is, first, I want to convert this into patches of 4x4. So how do you go from spatial 28 by 28 spatial dimension into 4x4 spatial dimension? So 4x4 spatial dimension means I have 4 patches. So along the height and 4 patches along the width. How do you go from 28 by 28 to 4x4? You can do two things. One is you can use a filter of size 1 by 1. Okay. And you can use a stride of 7. It is possible. But then what's the problem? You lose a lot of information because 1 by 1 filter, if you are jumping by 7 pixels at a time, the pixels in between you are not considering. Right? So instead of using 1 by 1 pixel, 1 by 1 filter with 7 stride, you pick 7 by 7 with stride equal to 7. So initially your filter will be here. And you need non-overlapping patches. Patches should not overlap. So that's the reason why we pick stride like this. So then after second stride, it will be here. After third stride, it will be here. After fourth stride, it will be here. So then your filter size should be what? Your filter size should be 7 by 7. And stride should be 7. That much is clear. If you use filter size of 7 by 7 and stride 7 on an input image of 28 by 28, you will get 4 by 4. Now 4 by 4 what? 4 by 4 patches. Now tell me this. What is the dimensionality of each patch? Each patch is equal to 1 token, correct? So what is the dimensionality of each patch? It's not one. Okay, patch has X, Y, and Z dimension. Tell me the spatial dimensionality of each patch. Spatial dimensionality of each patch. I'm not talking about 16 patches, each patch. Each patch is simply 1 by 1. This is one patch. Spatial dimensionality is 1 by 1. But how many channels does each patch have? (32 channels. It's not one channel because each patch we are now converting into a 32-dimensional vector. So now each patch, it will look something like this. So this is patch number 1. Let me just clean it up a little bit. So assume that this is 32. I'm just copy pasting it 4 times. So this is patch number 1, patch number 2, patch number 3, 4, like that. Now I have totally what? 16 patches. Each patch has a dimensionality of 1, or if I write it in the language of number of channels, comma, width, comma, height, it will look like 32, 1, 1. Each patch has 32 number of Z channels. It has spatial dimension of 1 by 1, but I have totally 4 patches in height and 4 patches along width and 4 patches along height. Now, tell me how many filters do I need now? So this is the filter dimension that you have agreed. 7 by 7 it should be the filter size. And you can, this is obvious also, right? See, the 7 by 7 filter will be standing in front of another 7 by 7 set of pixels. So those 7 values can just have a weighted addition, right? To just produce one number. But like that, how many filters should I need? I will need 32 filters because I have 32 channels at the output. Let me clarify this once more. Maybe I can draw proper rectangles this time. So my initial image is not RGB image. I'll tell you what to do if it was an RGB image. If it was an RGB image, it will look like this. So RGB 28 by 28. Now my kernel will look like, since I have 3 channels, kernel will look like 7 by 7, but it will have 3 channels also. 7 by 7 by 7. And like this, let me just group this. I will require, let's say I had 2 filters like this. If I had 2 filters, my output will look like 1 by 1 by 2. And like this, I will have 4 by 4 outputs. 1, 2, 3, 4. This second row, third row, and fourth row. Now think about this. If I had an RGB image, this is what would have happened. Okay, let's go backwards. How many patches do I have here? What's the patches distribution? It's 4 by 4. I have 4 patches along the row, 4 along the column. Each patch is of how many number of channels? 2 channels. This is 2 channel, 2 channel, 2 channel, 2 channel. Right? This is the first channel. This is the second channel. What is the spatial dimension of each patch? 1 by 1. 1, 1. So each patch is 1 by 1, but they have 2 channels. Why are there 2 channels in these patches? Why did it become 2 channels? Because there are 2 filters. But there are 3 here. So why do you say 2? What is this 3 then? Those are 3 channels. Why do you need 3 channels? Because you have 3 channels at the input. But these 3 channels combined form filter number 1. These 3 channels combined form filter number 2. This filter number 1 will produce this guy, will produce this guy, this guy, this guy, etc. So filter number 1 will take care of these top channels. Filter number 2 will take care of bottom channels. Now, what is the only change? I want to, let's say at the output, I want the exact same thing. Okay. This exact same thing I want at the output, but my image happened to be black and white. What is the only change I have to bring? At the output, I want the same thing, but input happened to be an instead of an RGB image, black and grayscale image. Then only change I should bring is I don't need 3 channels here in the filter. I just need 2. So sorry, I just need 1 with 2 filters. So I can just remove this and just have a filter of number of channels 1. Spatial dimension will still be 7 by 7. That's it. So this is the only difference. The difference when you have an RGB image versus a color image is the number of channels in your filter. Now, in our case, the actual dimensionality at the output that we are expecting, let me just delete this, is something like this. This is 4. Let's assume that this is 32. Let's assume that the channel size is 32. Okay, so now I have my output. There are 16 patches. Why are there 16 patches? Each image was 28 by 28. We were dividing it into, we wanted to divide it into 7 by 7 patches. So 28 by 28 is image divided into 7 by 7 patches. Each, you will have total 16 patches. But yes, there are 16 patches, but here we are representing each patch as a vector of 32 dimensions. A vector of 32 dimension, you can also imagine to be an image of spatial dimension 1 by 1 and z stack 32. Basically, it's a 32-dimensional vector, but here we are imagining it to be an image of 1 by 1 spatial dimension and 32 dimensions along the channel. So totally, you have 1 by 1 by 32. An input image is not a color image. It's a 28 by 28 black and white image, which means if my kernel size is 7 by 7, I will have just how many channels in my kernel? In each kernel, how many channels do I have? 1. Why is that? Because my input has only one channel. It's not RGB. But like this, I will have 32 kernels. Kernel number 1, 2, 3, etc. up to 32. First kernel will produce these outputs. Last kernel, 32nd kernel will produce these outputs. Okay. So this is what we are going to do. But this much, if I did not explain, you will not understand what I'm going to write in the next line. So self.patch embed is equal to nn.con 2D. So here we are performing a convolution, 2D convolution. And we need to define the number of channels. Number of channels is 1. And number of channels will define, number of channels in the input will define number of channels in my filter. Then I have to define my token dimension. Token dimension will define what? Dimension will define the total number of filters I need. Then I will define my kernel size underscore size. Kernel underscore size is nothing but patch size, which is 7. Then stride is equal to 7, which is same as patch size. If filter is 7 by 7, then the stride can be less than 7. Won't the patches overlap? Yes, correct. If filter is 7 by 7, if stride is less than 7, patches will overlap. So we should not use overlapping patches. That's the reason why here stride is 7. It's not less than 7. Now tell me this. My output will have certain dimensionality. Actually, we can see that what the output dimension will look like. Let's first write this function. Okay, so now we have the patching algorithm, but we have not implemented it yet. Now, in all the 4 parts, part 1, part 2, part 3, part 4, we'll be defining a forward pass. So in the forward pass, we are passing the self. So this self we are passing everywhere. Along with that, we are passing x, where x is the input. So define forward, and into that we pass the self. Self is the current object corresponding to the class. X is the input. To this, we say x equal to self dot patch underscore embed of x. So what happened to x? X was the input, which originally will be the input image itself. It will undergo patch embedding. Now x will become something of dimension. Let me go back to my whiteboard. The input dimension of x was 64, 1, 28, 28. 64 was the batch size, 1 was the channel dimension, 28 was the image height and width. After going through my current batch embedding formula, this will become 64, 32, 4, 4. Where 68 is the batch size, so that part remains the same. 32 is the dimensionality of each token. So this is token dimension. 4 by 4, because I will have an array of 4 patches along the row, 4 patches along the column, because 28 by 28 was a 2-dimensional thing. 4 by 4 is also 2-dimensional. It's just that this 28 by 28 guy only had 1 channel, but this 4 by 4 guy has 32 channels. That's the only difference, right? So please note this. This 28 by 28 became spatially, it became 4 by 4, but each 4 by 4 is now like a 32 channel thing, where you just have one in each of the patch, you have just one spatial 1 by 1 as a spatial dimension. So what we really have to do is, we don't care about having patches arranged as a two-dimensional array. We want patches as a sequence of 16 items, right? And then as the 0th item, we add the classification token. So what we have to do is X should now become, so now after patch embedding in this, it will become 64, 32, 4 by 4. But I want X to become initially 64, 32, 16, because this 4 by 4, I just want as an array of 16 items. I don't want it as a 2D array or anything. So here, what we can do is X equal to X dot flatten of 2. So what happens is everything starting from the second dimension will be converted into a single one-dimensional thing. So this is 0th dimension, this is first dimension, and this is second dimension, and this is third. So if I say flatten of 2, this, whatever is there after this, will be converted into a one-dimensional thing. So 4 by 4 will become 16. But that is not yet enough. I need to do one more thing. So I have batch 64 items in each batch. Then ideally, I should have 16 tokens. Then ideally, I should have 32 dimensions per token. But here, this is flipped, 32 and 16. I want ideally the token dimensionality to be here and the number of tokens to be here, not like this. So ideally, I want 16 to be here and 32 to be here. So this we can easily do by transpose. So now we say X equal to X dot transpose of, we are transposing, 0th dimension is untouched, first and second dimension we are transposing, so 1, 2. And then we say return X. So now what will happen is X would have become, so because of the first operation, X would have gone from 64, 128, 28 to 64, 32, 44. Then after flattening, so this is the con 2D operation. Here there are learnable parameters. Where are the learnable parameters? Can anyone tell me where are the learnable parameters found in this? Because here the patches are being converted into vectors, but it has to be found somewhere. It is found here. These are learnable parameters. In each of these 32 kernels, you will find your learnable parameter. Each kernel is 7 by 7. If you have 32 kernels, and if you have 7 by 7, learnable parameters, assume if batch size was 1, would be 7 by 7 by 32. Then here you do flatten, and then here you do transpose. So now you get 64 batch size, 16 as the number of tokens per batch, per image, and 32 as the dimensionality of each batch. Otherwise, you will be looking at 64. This is the logical representation, right? You have images first, then batches contain image, image contain patch, patch contain token. So first item should be batch dimension. Second item should be number of patches per image. This third item should be token dimension. But here right now it is batch dimension first, token dimension second, and number of patches third. So that's why we are doing the transpose. Okay, so now I could have done this just by saying X return patch dot embed of, I could have written it like something like this: patch dot embed of X dot flatten of 2 dot transpose of 1, 2. But then the problem is, if I had written this, nobody will understand anything. It's just one line, but there is so much going on behind this one line. So that is the reason why I split it into 3. Okay. And with this, our patch embedding class is done. That's it. Now you can just run this to make sure that there are no syntax errors or anything. But right now the class will not do anything because we have not instantiated it with an object. Now we write the class for transformer encoder. And obviously there also we pass nn.module. And then we define these two things. So these two are common for all. So I can just copy paste. Now in transformer encoder, what all things do I have? I have layer norm 1. I have layer norm 2. Then I have multi-head attention. Then I have multi-layer perceptron. One more thing is there, which I did not discuss in detail. One small thing. Dropout, let's say we don't have to do dropout. CLS token, we have not done yet. Position embedding, we have not done yet. But in the transformer encoder, there is one more thing, residuals. Where are the residuals? These two connections. Whatever comes here also has to pass here. And whatever comes out of this also should go here. Okay. So we should have those two residuals. So let's first define these things. Self dot layer norm 1 equal to nn dot layer norm. And layer normalization happens along the total number of dimensions in my input token. So this should be such that token dimension, whatever is the token dimension, that many number of normalization parameters will be constructed. So we just pass the token dimension here. Self dot layer norm 2 is also exactly the same. So we can just repeat it so that we have that many number of learnable parameters. So layer norm 1 and layer norm 2, we are just defining it. We are not yet using it. Then self dot multi-head attention equal to, so here is where we actually utilize Python's, nn dot multi-head attention, this function. If we did not have this, we would have had to define the whole thing from scratch, which is an unnecessary thing because they already have defined the class. We just need to train it by defining the token dimension and number of heads. So token dimension is 32, number of heads, if I remember, is 4. So self dot multi-head attention equal to nn dot multi. So now wherever you see nn, those are all trainable parameters. nn dot com2d, there are trainable parameters. nn dot layer norm, trainable. nn dot layer norm, trainable. nn dot multi-head attention, trainable. Then multi-layer perceptron, self dot MLP equal to, so now here in multi-layer perceptron, you have input layer, hidden layer, and output layer. So nn dot sequential, so you can add layers in sequence. And first layer is a linear projection from your input dimension to hidden dimension. So input dimension is token dimension, and hidden dimension variable was MLP hidden dim. So that is the hidden dimension. In between, there is a activation function. It's not ReLU, it's JLU, what is used in the vision transformer paper. You can see that here. So JLU is very much like ReLU. JLU graph, it's just smoother. So ReLU is the sharp version. This orange, JLU is this blue smooth version. It's a smoother differentiable function. And in vision transformer paper, if you look at third or fourth page, yeah, so here they say MLP contains 2 layers with JLU nonlinearity. So that is what we are adding here. NN dot JLU, and then you have another linear transformation from hidden dimension, MLP hidden dimension, to token dimension itself. That's it. So that is MLP. MHA is done. MLP is done. Residual is not done. But residual we can define. We don't have to. Residual we are implementing. We are not defining. These we are defining, because these layers, after training, these layers we'll just have once. But then once you have these layers values fixed, you have to execute it on each token. That's the reason why we are writing the separate forward function, because into this we are passing each input. Now in forward, we can say residual 1. Here I'm storing X. Then first is, let's go back to our image. After I'm storing the residual X, I have to go through layer norm 1. So X equal to self dot layer norm 1 of X. Then after layer norm 1, I'm going to multi-head attention. Then X equal to self dot this guy multi-head attention of. Now here I have to create query key value space. And the way you can pass X is one so that you can construct query, one so that you can construct key, and one such that you can construct values. You pass the same X. And the final context vector will be found in the output of this in 0th index. So you have to put a 0 index here. So in the 0th index is where you will find the output that you require. The output that you require is the final context vector matrix. And then in the image, you have residual added. So now you add X equal to what? X plus residual 1. So with these 4 lines, you have finished norm, multi-head attention, and this residual addition. Then you say residual 2 equal to also X, and X equal to self.mlp of X. So it goes through MLP. Actually, there is layer normalization. X equal to self.layer norm 2 of X. X equal to self.mlp, and then X equal to X plus residual 2. So now I have residual 2 also added. This part is now the residual plus layer normalization plus MHA. This is now the residual plus layer normalization 2 plus MLP. And then we return X. And that ends the transformer encoder part. So layer normalization MHA followed by addition of residual, layer normalization 2 MLP followed by addition of residual. Now we can, we have not added 2 things yet. I'll just explain what is this. So we need X is getting converted into query, key, and value. And here the way I'm pretty sure this can be done in a separate way also, but X comma X comma X means the same X is sent for converting into query, same for converted to be converted to key, and for value. So that is why we pass X 3 times. One to be input so that it can be transformed to query, sometimes to key and sometimes to value. I think the reason why this is done is sometimes in, for example, there is a concept called visual BERT or VLBERT, not visual BERT. In VLBERT, the query is from the text, but from the key and value are from the image. So then if you use the same X for query, key, and value, it will not work, because in my multi-head attention, I want query to be coming from image and key and value from text. And similarly, for text, I want query to be coming from text and key and value from image. So I think that's the reason why they designed it like this. And the reason why this index 0 is there, because at the end of the day, we want the context vector matrix, which happen to be stored in there, whatever is returned from this function. In that return, in the 0th index item is where we see the context vector. That's the reason why I put 0. Will X also contain patch for CLS token? Yes, X will contain patch of CLS token. Only thing is we have not defined CLS token yet. I will show you where we do that. Okay, now let's go on to multi-layer perceptron MLP classification head. This is the easiest. So class MLP head of nn.module. Again, we need these 2 things. We need constructor for the same class and for the parent class. This part is very simple. So one thing that is actually a bit confusing, which because of the way in which this figure was constructed in the paper, is that there is a additional layer normalization happening over here. In the multi-layer perceptron head, there is one layer normalization happening. It's not shown here, but it is mentioned in the paper. So if you go to the paper, this one I was initially confused. What is this layer normalization of? So this is now the context vector corresponding to classification token, which is why it's 0, after Lth transformer block. So there is a layer normalization happening to the context vector corresponding to the classification token before just before you go through classification head. But this was not shown in the image, so it will be very confusing if you just look at the image but don't read the paper. So that is the reason why I will add or define a layer normalization here. So self.layer norm but this layer norm is not shown anywhere in the image. Ideally, if I were making this figure, I would have just shown maybe one layer normalization somewhere here. That way it's less confusing to the people who are coding. Yes, two things we have not done yet: position encoding and classification token we are yet to define, but I'll show you where to do that. Self dot layer norm equal to nn dot layer norm of token dimension. Then what else do we need? We need one sequential linear layer. So self dot mlp equal to nn of linear between embed dimension to number of classes, right? So nn dot linear of embed dimension is same as token dimension and num classes. So here we project from a 32-dimensional vector to number of classes. I don't know what was the variable name. Yeah, number of classes. So here we go from 32 dimension to 10 dimensions. And then we define forward. So define forward of self comma x. And here we implement x equal to self. So this is Gemini's suggestion, what is popping up, but I'm just ignoring it. I'm writing the same thing only, but it'll be fun to write from scratch. Then x equal to, so here what we should do is x equal to self dot mlp of x, and then return x. Now we are ready to, now this x is what? By the time we are returning, what is this x? Forward spelling, yeah. Multi-head attention encoder block. Multi-head attention block will be too much for this lecture. I highly recommend you to look at the previous lectures because it will at least take me 1 hour. But this return x is the 10-dimensional vector, which we can use for, yes, exactly, logics, perfect, which we can use for softmax, right? Now let us combine all of this. Class vision transformer of nn dot module. Again, same two things, init constructor and the parent class init constructor. Now here we will do all the things which you have been asking. So first we have to do patch embedding. So let's define patch embedding, self underscore patch embedding equal to whatever is this class name. Where is that? Patch embedding. So this will be the patch embedding. Then self dot. Now we have to define CLS token. We have to define position embedding. We'll come to that. Position embedding. Then we have to define transformer blocks. Because we have multiple transformer blocks, we have only defined one transformer block here. So self dot transformer blocks equal to this. We have to define CLS token. We have to define position embedding. We have to define then self dot MLP. What was it called? MLP head underscore head. This is already defined. It is simply MLP head. So this is the classification head. Then what else we have to define? I think that's all. Classification is also done. Now let's look at the classification token. Classification token should have a dimension same as input embedding dimension, but it should have random numbers initialized, and it should be learnable. So because it's learnable, it should be nn dot something. So it is nn dot parameter. This is a learnable parameter. Then torch dot randn, which means we are pulling from a random distribution. Here we don't need dropout for this data set. At least let's ignore dropout for a moment. But ideally, if we were training for a bigger data set, I will definitely introduce dropout in multi-head attention. I'm not 100% sure if we can directly pass a dropout parameter here and dropout is taken care of inside this or not. I have to check that. I assume it will be possible. Dropout is a way in which you prevent overfitting. All right. So MLP head, what was the torch dot random number from a normal distribution, and dimensionality is you have embedding dimension, but your patches, you had 16 patches. You had a 64 was the batch number. You had 16 patches. Each patch was of 32 dimension. You had 3 numbers to take care of. So you should have 1, 1, embed dimension. I'll tell you what to do with this, but I should have 3 items as part of dimension here. And this should be token dim, I think, in my variable convention. I'll tell you what to do with this. So right now I'm defining a classification token which has 3 dimension, and third dimensionality is where the parameter is coming. Then position embedding should be, again, it should be parameter. So nn dot parameter of torch dot rand n of something. And if I had one batch, I'll have 1 dimension for that. But here, what should be the next number? What should be the next 2 numbers, in fact? Position embedding, I'm defining position embedding, patch size and token dimension. Is it that, or position embedding is added to every single token? Correct? So it should be number of tokens plus 1, isn't it? Total number of tokens plus 1, because I have 1 position embedding for class token or classification token also, not just for rest of the tokens. So num, I don't know what was the variable name. I think it's called num patches. Yeah, num patches plus 1, comma, last dimension will be token dimension, because position embedding is also of dimensionality 32. Then number of transformer blocks. This we can write in 2 ways. nn dot sequential, I can write it like nn dot sequential of what was the name of the class? Transformer encoder. And what was the number of heads? I think it was 4. Yeah, number of transformer blocks was 4, which means I could write it technically like this. This comma, this comma, this comma, this 4 times I can write. But then what if I had 32? I cannot build it like this sequentially. So then the better way to do that is put enclose this in square bracket first. Put star here at the starting, and then define a for loop. So transformer encoder for no variable name. So for underscore in range of whatever is the number of transformer blocks. So num, not num heads, transformer underscore blocks, I think. Yeah, transformer underscore blocks. So basically, I am looping a for loop 4 number of times, because the value of this is 4. And there I'm adding this transformer encoder sequentially. And this is the syntax for that. And MLP head is also done. So now there is one problem. The problem is my batch size is 64. So I need 1 classification token for each batch. I mean, each set of images should have 1 classification token. So if I have 64 images in my batch, I should have 64 classification tokens, right? But that is not provided here. Star basically does, that's the convention that is followed. Essentially what we are doing here is we are attaching 4 transformer blocks sequentially, so transformer encoder blocks sequentially in series. All right. Then we say, now we have defined these things, but we have to implement, we have to execute it for each token. So self define forward of self comma x. And then we can say, first we have to perform patch embedding for the token x equal to self dot patch underscore embedding of x. And then CLS token. So CLS token, what we need to do is CLS token equal to self.cls token dot expand, and we are expanding it along the batch dimension. So batch dimension is the first item. So then batch underscore size, comma, then the rest of the dimensions are untouched. Because I need if I have 64 batches, this first item should be 64. So I'm expanding it to fit the batch size. I'll tell you, there is one problem here, by the way. Can anyone tell me what might be the problem with this? The problem is specifically with respect to using batch size. If I directly use batch size, there is one small issue. Shuffling is fine. Of course, I'm shuffling. So here what we are doing is, see, CLS token is added to every single group of patches. Every single 16 patch should have one CLS token. But do I have 16 patches? No, I have 64 batches. In each batch, I have 16 patches, which means for each batch, I should have 64 CLS tokens, right? So the first dimension here should be 64. Remaining can be as such. So I don't have to expand the remaining dimensions. So this has to expand. So now the problem here is, if I directly write here batch size, what is my batch size, by the way? If I had 640 images, and if batch size is, let's say, 64, totally how many batches can I have? 10 batches, right? But what if I have 639 images? Then my last batch actually has how many images? It has only 63 images. It does not have 64 images. One image is less, which means instead of directly using batch size, it is better to use whatever is the actual batch size of that image. So I can just say number of images in current batch equal to x dot, we can take the x dot size of 0. Shape of 0 is also fine. X dot, yeah, actually shape of 0, let's use this. So the 0th dimension of my input, which is the actual number of images in my current batch. In all the batches, it will be 64, except the last one, because I don't know if the total number in my training data is exactly divisible by 64 or not. And this will cause a problem. And then this number, this variable I can use here. I can just use b or something instead of this huge thing. So b comma -1 comma -1. You can try running without this. You can try just running with batch size. You will run into some dimensionality issue. And now let's do one thing. Let's add position embedding. X equal to torch dot, we are performing concatenation, and nn dot parameter. So can you tell me one thing? I need 64 classification tokens for each batch. Should I also not expand position embedding to fit the batch size? So here I'm going to concatenate position embedding to, so x equal to torch.cat of CLS token, comma, x along dimension equal to 1, not along the batch dimension, along the batch dimension. But my question is not this. My question is x equal to x plus self dot position embedding. Should I not repeat position embedding also along the batch dimension? The reason is position embedding, we don't have to learn it proportional to batch size. Position embedding, it is learnable for sure. It's a learnable parameter, but it doesn't matter whether you are in image number 1 or image number 63 in the batch. Position embedding, position is still the same, 1 to 16 or how many ever number of token patches you have, right? So I don't have to expand it. I don't have to have 64 different position embeddings. I can just use the same position embedding. Okay, so position embedding is done. Then you pass through. Now you have the ability to pass through transformer blocks. So x equal to self dot transformer blocks of x. Then after that, you have to pass through multi-layer perceptron, which is the classification head. Is there any mistake here? In this, is there any mistake? Exactly. From all the batch, I should only extract the classification token. So from all the batch, which is by x of colon, I'm extracting 0th index item in the second, in dimension index number 1. And then only I pass it to multi-layer perceptron for classification. And once this is done, I can simply return x. All right. So that is also done. So now we have vision transform, and let me just run this to make sure there is no syntax issue or anything. So now we have all the three ready, and now we can define some things for our training. So device equal to CUDA, all those things we can define, model, optimizer, just 3-4 lines. So now most of the hard work is done. Now it's simple. And loss. So device equal to torch.device.CUDA if torch.CUDA is available. Else use CPU. Then model equal to model. For that, we just need to call this. So vision transformer dot to device. So whichever device we are using, GPU or CPU. Then optimizer, almost always we use Atom. Torch dot optim dot Atom. Into that, we are model parameters is what we are optimizing. Model dot parameters, comma, LR equal to whatever is the learning rate variable we have defined, which we had defined at the beginning. And criterion will be cross entropy loss. So that's it. Torch.nn.activation. Let's see where is the issue. I might have missed to import certain libraries. Let me just check. Vision transformer has no parameter. It is parameters. In that con 2D, I think the issue is D should be small letter if I'm not wrong. Yeah, that D should be small letter. That's why. C should be capital, D should be small. Okay, that was a minor issue. So what I was missing was I was missing parameters. That was one thing. And in JLU, I had forgotten to put this functional bracket. That was the other thing. Those were the only errors that I had. Okay, now we can define the training loop. So now in this training loop part, it's not specific to vision transformer. It's for any code. So I would rather open my own collab from earlier. because training loop is not fun. It's just manual effort. Okay, so here what we are doing is we are running over 5 epochs, initializing loss and total number of epochs and how many we have gotten correct into 0. And I just want to make sure that here we are using the same variable name, train loader, images, labels, optimizer, outputs. I think variable names are fine. If I just run this, it should hopefully work. Yeah, now it is running. Yeah, this code I'll share with you guys. I'll just directly put it in the chat or maybe in gist. So the training part, you can just pick the code from here because this is not vision transformer specific. This is for any ML model. You simply run, calculate how many you have gotten correct, and for each epoch you print the accuracy. So here there is nothing transformer specific. But do you see my accuracy? It is really, really bad. And this whole thing, I know why this happens. It's just due to one single mistake. The single mistake is in just one line of multi-head attention. So in multi-head attention, where is that? In self.multi-head attention, we have to say that the first dimension that it is expecting is the batch dimension. So here we have to say a parameter called batch first equal to true. So I'll change the parameter, I'll stop the training, and I'll train this one more. See, 10% is the worst model, right? 10 class classification, random, this is like random picking, worst model. But now with that batch first, let me run once again, I'll show you the accuracy. See, it's much, much better, 95, 92%. So that batch first, yeah. So batch first is the multi-layer perceptron expects the first dimension that you are inputting bunch of things, by the way. You're inputting batch, you're inputting a sequence of tokens. You are inputting for each token, there is an embedding dimension. And you have to explicitly say that to the multi-head attention, you have to explicitly say that the first dimension is batch. Otherwise, it will take first dimension to be the to be instead of 16, it will think that 64 is not the dimension of the batch. It will consider first dimension as the sequence dimension, which is I think the number of tokens or something. But here the first dimension 64 is actually batch. So we are already passing batch as the first dimension. So this batch first equal to true will take care of that. Actually, in the last lecture, which I posted regarding implementing multi-head attention without using for loops, I had very nicely done a calculation of how to convert your dimensionality such that you are looking at items per batch by taking some nice transpose operation. So I will share that video is actually available. It's called Implementing Multi-Head Attention in Practice or something like that was the title of the video. You can just check on our channel. Yeah, I'll share actually this code I can share directly with you because this is also common. It's not specific to vision transformer. It's for any deep learning. But you see the accuracy now, 95% in just 5 epochs. And now I have one more code. Yeah, accuracy increased because earlier I was not explicitly telling my multi-head attention that the first item it has to consider is the batch dimension, first dimension. So that was missing. So now I added batch first in the multi-head attention as the third parameter. Then the next thing is type error. 2 tensor object is not iterable in training loop. I think if you share screenshot, it will be better. I think maybe some function bracket might be missing. Then what else? Yeah, just validation accuracy. This is again, you just pass it through validation data set. And so you are using val loader instead of train loader, and you can just print the validation accuracy. So I don't want to go through this code because this is not vision transformer specific at all. This is for any neural network training. but validation accuracy is 96.21. We can just see one more thing. I'll paste the validation accuracy here, but please paste it. Please use these codes separately. I'm putting a giant space in between. Yes, I will share the vision transformer once. So this is vision transformer. The only thing in vision transformer, I did not change anything, but I had patch embedding. So these things are to be defined wherever trainable parameters are there. And wherever you have repeated execution over tokens, you put it in this defined forward function. Then last thing, which will be cool thing to see, is just randomly predicting on some random images from your validation data set. So here I am again calling val loader. I'm randomly picking 10 items and I'm just printing what the predictions are. So now these are the images, prediction and reality. It will mostly match. It's very difficult to find mistakes here because the accuracy is very good. But if we did not have this this loader, if we did not have this batch dimension first, this will not work. Now let me see what kind of errors you guys are keeping. All codes in. Yeah, I will share all the code for you guys pro members. But what other errors are you getting? I think this 2 tensor image might be criterion is not defined. Did anyone manage to get the code working? That's a, I guess, more important question. Okay. And what about accuracy? Is it 95-ish, 95, 96? Okay, excellent. Okay, now some issues are about cross entropy loss issue. Patch embedding is missing the required forward function. Okay, so forward function, this forward function is there in all the 4 classes. We have 4 classes. Okay, so forward function is there in all the 4 classes. Please don't miss that. And in this init constructor, it should proceed with 2 underscores and it should have 2 underscores after. Please check that. And you have 2 init constructors, one for the class itself, one for the parent class. Transformer underscore blocks is not defined, probably because this part is not executed yet. Now let me share this part of the code also just to display some images. This will be fun. Yeah, just use this code also just to display some random images for your. Yeah, I will show my MLP head class. MLP head is actually the easiest class. It has just layer norm and one linear projection from 32 dimensions to 10 dimensions. One thing we can try here is this. What if I did not have multi-head attention? What if I had a single head attention? Then number of attention heads will be 1. What if I had 1 transformer block? Let's keep it that way. What if my token dimension is really bad, 3-dimensional token? And what if my MLP hidden dimension is only 6? And batch size, let's keep it that way. So now see, I'm having a very bad transformer architecture. Let's see what the accuracy is with this kind of a setup. I'm very curious. I have never tried this myself, but not great, but 27, 30. So 1/3 of the items hopefully should be correct in my validation data. Okay, and so this is the worst transformer architecture. Okay, and you can clearly see that it's making mistakes. So here prediction is 0, but true is 2. Prediction is 7. This is actually 4. Some of the easy ones are getting correct. And then here we can do some sort of ablation studies. We can just change some items here and see what works best. Let's say I don't want multi-head attention. I want single head attention. Token dimension I increase to 32. MLP dimension I increase to 64. Transformer blocks is 1. So let me see how this works now. So instead of 3-dimensional embedding, I have now 32-dimensional embedding. And I think this will be better. Yeah, you see, I don't even have a multi-head attention. I just have single head attention. It works kind of well. Not as good as early, but kind of well. All right. So this is good. I just want to see where it is making mistake. Yeah, only difficult images it's making mistake. Rest of them are kind of straightforward images. This is an easy image in my opinion, but see, the prediction is sensible, right? It's 4, it's getting classified as 9. Here 9 is getting classified as 4. Here 5 is getting classified as 6. It's making sensible mistakes, not like senseless mistakes. All right, so this is pretty much it. Now, we haven't explored yet. If we need only CLS token, why are we still calculating context vector for all patches? Because you can't calculate context vector just for one query, right? You calculate context vector, you calculate attention weight matrix. And using attention weight matrix, at the end of the day, we are only taking the context vector from the CLS token over here. Where is that? In the vision transformer class, we are only taking finally CLS token, this one. But for constructing the context vector for any token, you need the whole attention weights matrix. Because context vector is equal to attention weighted average of your value vectors, which means you need attention weights matrix to produce the attention weighted average of value. Not attention weighted average, attention weighted sum. Attention weighted sum of value vectors is a context vector. How is CLS token helping in classification? Could you give intuition? So in vision transformer paper, actually they tried, you can think of it this way. CLS token has some parameters that are learnable. Now, how does this learnable parameter values evolve? It evolves in such a way that if CLS token was not doing a proper classification, the error due to the learnable parameters inside the CLS token will be so high. So naturally, CLS, the weights and query key value weights inside the transformer head will adjust in such a way that the CLS token value will become so favorable towards classification. Now, if I were to try this for the very first time, and if BERT model was not existing, I don't know if I would have tried CLS token as the first thing. What I would have tried was, I would have tried using all the other tokens somehow, maybe creating a combined embedding using all the other tokens context vectors, and I might have tried classifying. In vision transformer paper, they mention it somewhere. Let's see, class. I think somewhere in the supplementary. Yeah, similar to BERT's class token, we prepend a learnable embedding, which serves as this both during pre-training, but not here. I think it's somewhere later. Yeah, you see this? In order to stay as close as possible to the original transformer model, we made use of an additional class token, which is taken as image representation. So this class token contains the whole representation of the image. The output of this token is then transferred into a class prediction via a small multi-layer perceptron. This is the MLP classification head with tan H nonlinearity in the single hidden layer. So here I think they are mentioning about some other variant. Otherwise, it is JLU. This design is inherited from transformer model for text, and we use it throughout the main paper. An initial attempt, so read this sentence, an initial attempt at using only image patch embedding, so without CLS token, using global average pooling them, followed by a linear classifier, similar to the MLP head, just like ResNet final feature map, performed very poorly. However, we found that this is neither due to extra token nor due to gap operation. So here, actually, they have done 2 experiments. So these 2 graphs are this orange one and green one are without CLS token. And in one case, they saw better accuracy. In other case, they saw worse accuracy. But they're saying the accuracy difference was not due to CLS tokens presence or absence. It was due to the learning rate difference. So in my, can you see this PDF? I'll just share the, okay. So in my intuition, I don't have a great intuitive answer for why CLS token is 100% needed. I can understand what CLS token is doing. It is creating a representation, a vector representation of the whole image, just like how the last context vector in text is creating a vector representation of the whole sentence or whole context window. Same thing what CLS token is doing. But can we work without CLS token? In my mind, I don't see any issue, just like what is shown here. You can work without CLS token also. Can we pick any context vector from any random patch for classification? That probably not, because we don't know what each patch is attending to. Maybe some patch is attending more to some other patches. So just taking one single patch representation might not give you, but these guys are doing pooling, global average pooling from all the patches. So they are not just using one image patch embedding, all the patches. So if we implement something like this, where we somehow pool the values from all the patches, it might be better. Is this due to gap being not learnable? No, I mean, patch embeddings are anyway created as a result of learnable weights, right? So I don't know if that is the issue. And I don't see the issue, honestly, by the way. This green color graph with smaller learning rate is working better. Maybe the issue is that with smaller learning rate, it will be slower. You will need more computational time. But other than that, I don't see too many issues in trying in some cases without the CLS token. I think the main reason why they would have started CLS token is because BERT used CLS token and they were biased by the existence of BERT, maybe. But in any case, okay, wondering if there is a reason why not use MLP as at the last token. MLP at the last, we are using MLP at the last token. What do you mean MLP? What do you mean why not use MLP? We are using MLP, right? Last token is passed through MLP classification head. Oh, I see. Instead of CLS token, use it on the last token. Yeah. That reason is because, see, in text-based in GPT, last token contained the whole context because of the masking. Here, there is no masking. So we have no idea whether which of the patches have the highest context. We don't know that simply because this is not a left to right model. So models where prediction happens from left to right are called left to right models. BERT was a bidirectional model. The name itself was bidirectional encoder representation or something from transformers. So, so of course, we cannot pick any patch and use that. That much is clear. The only question is, can we create a combined embedding just using the patches and use that for classification instead of using classification token? That is a smart question. I think we can. I mean, that's what this graph is showing. I don't see much problem. And then when they say like accuracy is very bad, if we try that for our MNIST data set, I don't think the accuracy will be that bad. I think it will be good. Can you please remove token and run? I mean, we can do that. We can try removing one of these tokens. Okay, that's a good experiment to run. So let me keep some of the transformer heads. Number of blocks is 4. Token dimension is 32. Channels is 1. Okay, all of this is fine. Now, let's say I did not have extra classification token. So I don't have number of patches plus 1. I only have number of patches. And CLS token is not needed, let's say. And this is not needed. And I'm concatenating. I don't need to concatenate CLS token. And let's say I'm passing some random token. Let's say I'm passing token number 1 to my MLP head always for classification. I think this code, I don't see any logical issue right now. So now I don't have the classification token anymore. I'm just passing the representation from token number 1 into my final output. Let's see what the output looks like. Not bad at all, actually. Excellent output, in my opinion. So in this data set, it looks like we can take some random patches embedding also. It's not 96%, but not bad. Is CLS needed if we want to perform object detection? Very good question. So object detection, we will have to formulate it in a different way. We will see that when we are working on different models like detection transformer. So by default, the vanilla vision transformer is not good for object detection because training itself is in a different way, right? The labels are like the bounding rectangle coordinates and the class score. But see this very, very nice suggestion. Whoever suggested not using classification token, very good suggestion, excellent suggestion, in fact, because I'm getting very good accuracy. I don't know if I'm doing something wrong here. It's so good. But this data set is also very small. I'm pretty sure this will not work for bigger data set. We can also try generating a random number. So, and then pick that. Or maybe now that I have almost 100%, 96% accuracy. This is crazy, right? I'm picking randomly this token number 1. Where is that? Here. I'm randomly sending token number 1 to MLP get. What if I send token number 4 to ML or 10 to MLP head? Let's see if this works. Yeah, I mean, all tokens are having good amount of context. This is what it means. We could take mean also. X equal to mean of x comma, how do we take mean along the which dimension? Along not batch dimension, along dimension number 1, right? This is also working really well. Let me just take some random, just randomly take mean and send it to MLP classification, right? And let's see if it works. Mean received invalid arguments. Okay, let's ask Gemini to fix the syntax. But this is cool. I really like this discussion, guys. The suggestion was really good. Suggestion to remove the classification token. I mean, really, really good. Yeah, now we are working with the mean. This is also working very well, surprisingly. I had not tried this, so thanks for suggesting to try this. Good to know. So this is just a normal mean. Okay, this is not even global average pooling. We can try global average pooling. Validation was also 96%. Last time it was 96. I'm sure this time also it won't be different. But let's stop after this. This was supposed to be a 2-hour workshop. It's become almost 3 hours. But I'm hoping that you guys are enjoying. But try this code, guys. I think this is very, very cool. We will meet again in the next week for Transformers for Vision series, guys. We'll be discussing. So there is one small plan change I have made. I initially wanted to talk about data efficient transformer and then detection transformer, and only before stable diffusion I wanted to discuss vision language model. But I have planned to change it to bring vision language model earlier, because that way you guys can directly understand VLM, because you have your understanding about transformers and vision transformers are fresh now. The code I'll be putting on the course dashboard, you can find it from there. But this is the validation accuracy, 96.1% without classification token. Thanks for suggesting this. This was very surprising. I thought the accuracy will be very bad, but it's good. But I'm sure this is also because data set is too simple. For other data sets, I doubt we'll have such a good accuracy. In any case, we'll meet again next week. Try running the code. It's not that difficult to get it running. You guys can try this on some other either CFAR 10 data set or some MNIST fashion data set, or slightly more difficult, like some smaller versions of ImageNet or something like that. Just try that, okay? Next week, we'll be most likely working on vision language model. I'm yet to completely finalize whether it should be that or data efficient transformer, but most likely it will be vision transformer, vision language model. So thank you so much, everyone. Code I'm posting in the full code of mine. I'm posting in the course dashboard. See you next week. Hope you enjoyed it. Please, please try the code yourself if you have not managed to get it working. I hope you learned about vision transformer. I hope you understand about transformer in a much, much better way now. And I hope you understand the idea behind representing things using vectors, representing sentences using vectors, representing images using vectors. At the end of the day, it's all mathematics if you really think about it. You're projecting it from a bigger space into a slightly smaller space. And then you are using that smaller space to produce output, either it's a classification or next word prediction, etc. So I hope you are slowly getting that intuition. By the end of the course, you will definitely have that. So let's meet next week. Thank you so much. Lunchtime. Bye. And you can see my screen all right. If you can confirm, that will be great. Okay, thank you. So welcome back to a new lecture from Transformers for Vision. We'll be building, and before that, we'll be understanding about vision language models today. After learning about VLMs, we will also build a NanoVLM completely from scratch. In the last lecture, we looked at building a vision transformers from scratch. So some of those ideas will be very beneficial for you here in understanding the architecture. And this is, of course, under the category of multimodal LLMs, because in vision language models, you have two modalities, the modality which carries vision and the one that carries text. So now let's look at what are VLMs. Ideally, VLMs should be able to process text and image data together. So if I write a word apple, or if I show you the image of an apple, in human brain, we process both of these kind of similarly. Both of these are represented by the idea of apple inside our head. So how does that happen, right? So somehow VLMs should understand that this and the picture of an apple both mean the same thing. Now, we can think of this in multiple ways, but one of the simplest ways to think of representation is how did we represent text in a large language model? What was each token becoming in a large language model? If you can answer in the chat. Each token was represented using dash. It was basically a vector, right? So each token was converted into a mathematical multi-dimensional vector. So we can think of a similar idea here. Somehow convert apple into a vector of n dimensions, and somehow convert this image of the apple also into a vector of the same dimension, same number of dimensions, and then figure out how to make these two representations close to each other or similar to each other. So if you look at this image, it very nicely captures this whole idea. So this is the vector of the text dog. This is the vector of the image dog. They should be very similar. Ideally, they should be close to each other because this is a semantic space, multi-dimensional semantic space. And each area of this space, when you are pointing a vector to that area, it has a specific meaning. So in general, you can think of vectors corresponding to animals pointing to the semantic space for animals, vectors corresponding to fruits like apple, orange pointing to another direction in the space. But what we want is, we want the vector embedding of the text of dog and image of the dog to be same. And this we have discussed many times in this course. How do we quantify similarity between two vectors if the dimensionality is the same? We take cosine similarity, correct? We can take the dot product and construct a cosine similarity. So if these two were unit vectors, so let's say I call this as vector z corresponding to text t, and this I call as vector z corresponding to image I. And if they are not unit vectors, I can just do divide by magnitude of I and take the dot product of zi with zt and divide by magnitude of t. And this will basically be cosine of theta I t, where theta I t is the angle between image and text representation. And if the vectors are very, very similar, the angle between them will be close to 0. And that would mean cosine of 0 will be 1. If the vectors are not at all similar, they will be orthogonal. Then cosine of 90 degree will be close to 0. So this is the idea. Now, you have already learned one way to convert your text into vectors in large language models. How do you convert text into vectors in large language models? What exactly did we do? If you can note down just the very first step, what was the very first step? How did we convert a text into like a word in a sentence? How did we convert that into a vector? Yes, we need tokenizer for sure, but we first need a dictionary, right? We need a vocabulary. So our vocabulary will have all the possible tokens that the language model will encounter. Now, if for simplicity we say that the tokenization is each word is one token, in reality, that's not the case. In reality, each token can be word or subword. But if we simplify and say that each word is a token, then the vocabulary will consist of all the possible words. Now, this vocabulary, let's say the first word is apple. Then there are a bunch of other words. Last words will be something else. Now each word will have an ID number 0, ID number 1, etc. And we also discussed that GPT-3 had around 50,000 tokens in its vocabulary. So it was like a relatively big vocabulary model. Now each of these tokens are represented by one vector. So token number 0 will have a vector associated with it. Token number 1 will have a vector associated with it. Token number 50K will have a vector associated with it. The dimensionality of this vector will depend on what your model is. So one of these was 768 dimensional model. It was I think GPT-3 model was 768 dimensional vector. And you can have any number of dimensions. So now if you are presented with a sentence like apple is a fruit, something like this, then the first thing you do is you will divide this sentence into tokens or corresponding token IDs. So let's say the token ID of the first word is 0. Let's say the token ID of this is 350. Let's say this is maybe this should be 0, this is 10. And let's say this is something like 100, something like this. Then we look at our vocabulary or dictionary to see what is the vector associated with token number 10. What is the vector associated with token 350? What is the vector associated with 0, 100, and so on. Thus, we will get 4 vectors of 768 dimensions, and each of those vectors will correspond to one token. So this is how we got vectors associated with a text. And then one more thing which we did was we added position embedding. So if the first token is at position 0, second token is at position 1, third is at position 2, position 3, and so on, we added position embedding to get the final vector embeddings corresponding to all input tokens. And only then we passed all of this through multi-head attention to produce context vectors. So this will go through multi-head attention. This will pass through multi-head attention. Each tokens will produce one corresponding context vector. And that context vector also had same dimensionality as that of the input. So if this was 768, this was also 768. So we went through this process to produce vector associated with your text input. Now, by slightly different logic, how can you convert your image into a vector? So text conversion to vector is something that you are familiar with. How do you convert your image into a vector? One example you already know from the last lecture. In Vision Transformer, you knew how to convert image into a vector. What did we do? We divided an image into patches. Each patch was converted into a vector, which was the token. Then on top of that, you added position embedding. Then the position embedded tokens were passed through a transformer to produce the final context vectors, right? So that is one way. Another way is you can pass the image through a convolutional neural network without any attention mechanism or anything. You just pass it through convolutional neural network to increase the number of channels of the image and decrease the spatial dimension. Originally, the spatial dimension will be, can you please prevent from drawing on the screen? Otherwise, I'll have to remove you. I'll share the screen once more. So each image at the starting will be 32 by 32 by 3, something like that of dimension. So XY spatial dimension will be 32 by 32, and Z number of channels will be 3 RGB. And as the image passes through each convolution layers, the spatial dimension will start to shrink, which I will show you in a moment, and number of channels will increase. At some point, you can have the image represented by just one vector. And if the dimensionality of the vector embedding from the text and dimensionality of the vector embedding from the image, if they are of same number of dimensions, then you can directly construct the cosine similarity. So this is in a nutshell how you could imagine constructing a, you can imagine constructing a simple vision language model. Yes, if the image has multiple objects, what is done in reality is first the image is passed through an object detection model like faster RCNN or something like that. Then that model will give you potential region proposals within the image. And those region proposals are then converted into vectors, not the entire image. In our lecture today, we will not be using any region proposal network or anything. We'll be directly using one image with just one object. But in general, the image entirely is not converted into a vector. The regions within the image are converted into a vector. To know what are the regions that are meaningful, you use something like a region proposal network or faster RCNN. I'll actually show you a paper. So there is this paper called Visual BERT. And in this paper, what they did is for each image, they constructed rectangular regions. So just see this. So here, this is just one image, but then they have this red color rectangle, yellow color rectangle, blue color, etc. And I just want to show you one sub image. Just focus on this last layer 11 image. Okay. I know that there are a lot of things going on, but I'll just show you quickly what this is. So red color is man, blue is shirt, yellow is sidewalk. This light red color is pedestrian, and then this blue is sidewalk. Then look at the color of these rectangles. This color of these rectangles are matched with the color of these squares. So here, essentially what that means is this column is corresponding to image embedding of this person or this man. This column, this third column corresponding to this yellow color is probably, I don't know what is that, sidewalk. Then let's say this light red color is what? Pedestrian. So light red color is pedestrian, and you see using the light red rectangle, it is enclosing some other pedestrians that are walking. And now look at the last layer, what they are visualizing. So last layer is the rows are the words, which is a caption that describes this image. So the caption that describes the image is man wearing white shirt is walking on sidewalk alongside other pedestrians. So just read these words from top to bottom. It is just one sentence. So they have divided the sentence into words, but it's just one sentence. Man wearing white shirt is walking on sidewalk along other pedestrians. Now, what they tried to do was they built a vision language model to see how much does the word man correlate with whichever rectangle is corresponding to man. So which rectangle corresponds to man? Red rectangle. So ideally, for the word man, this rectangle, actually, let me take a screenshot so that I can annotate. Yeah, this paper name is called Visual BERT. So here, ideally, the text corresponding to man and the image corresponding to man, they should have the highest similarity. So this rectangle should have the most intense color. But here you can see that in the first layer, so third layer of the visual bird, this rectangle also has some high color. So that is man as the text, and this light red is what? Pedestrians. So basically, when the text encoder is looking at man, the image encoder is looking at pedestrians. But by the time you reach the last layer, look at the last layer and look at this. So now this is man and this is pedestrians, and look at this color where man as the text and pedestrians as the image, they are kind of intersecting. Here there is no color. So by the time the model is into layer number 11, man is fully looking at just the man. See, this is the one with highest color. So the highest color is light color, like whitish color. So whitish color has 0.4 as the correlation score. If it is a dark square, it will be 0. So this is just the correlation map. And look at the mapping. Okay, I'll pick one more example. So let's say, okay, in the title itself, in the caption itself, they are mentioning a very good example. So the model also refines this understanding, incorrectly aligning man and shirt in the third layer. So let's look at third layer and how man and shirt are aligning. So third layer is this, layer 3, man and shirt. Which one is shirt? Light blue. So light blue, man and shirt are aligning. I don't see man and shirt aligning in third layer. Actually, I see shirt is blue, shirt is... Okay, actually, I don't see man and shirt aligning in layer number 3. Where is shirt and man aligning? Shirt is blue and man is this side, but here there is no alignment. This last one is pedestrians, right? So this is man. Oh, man wearing white shirt is walking along. White box, man and shirt is aligning. White and shirt. Yeah, white and shirt is aligning because white and shirt should align. I think they are, I mean, white shirt, it's okay. Dark means there is very little correlation. Bright means there is correlation. Let's look at another example. Let me just first remove these annotations. Which one should we take? Let us look at this one, this white. So this white is walking, the word walking, and pedestrians. So in layer number 4, the word walking and the image corresponding to pedestrians. Why is it pedestrians? Because this fourth column is pedestrians. That's why. Has very good alignment. But by the time you reach here, the word walking has very little alignment only with, I guess, man, because this is the row associated with the word walking. And the first image is man, second image is shirt, third image is sidewalk, fourth is pedestrian, and fifth is sidewalk. So basically, by the time of fourth layer, the model is a little bit more, I would say, careful in producing the alignment. Yeah, walking and pedestrian should align. In my opinion, walking and pedestrian should align. But I guess it's up to what the model is learning. There was actually one very good example. Can you please explain layers and column? Yeah. So each row corresponds to the individual word in the sentence. So man wearing white shirt. So that is each row. So now imagine that each row is now converted into a vector embedding. Each column corresponds to these rectangles where objects are identified in the image. So rectangle with red color is man. You can see that it's a man over here. Rectangle with blue color is shirt. You can see that this blue rectangle is actually enclosing shirt, kind of. It's also enclosing white. Yellow is sidewalk. I don't know if yellow is actually really enclosing sidewalk, but whatever. Pedestrians is light red, and you can see that other pedestrians are in light red. There are 3 pedestrians. There are 3 light red rectangles. Okay. So now the word pedestrians, actually, let's look at the word pedestrian itself. That's the best example. We don't have to look at anything else. Just look at pedestrians. The word pedestrian should be corresponding to 3 these red rectangles, correct? Which means word pedestrian and this pedestrian bounding rectangles should align. So ideally, the score inside this cell should be visibly highest. But in some layers, it's not very high. In layer 3, it's not very high, denoted by the dark color. But by the time you reach the last layer, actually, you can see that this is pedestrian and this is pedestrian. It is aligning, kind of. And what are the other words? Side, other. So other means other people, right? So other word should also align with ideally pedestrians. And here, actually, there is no alignment in layer number 3. In layer number 4, there is no alignment. In layer number 5, there is some alignment. Layer number 6, very little alignment. Layer 10 has very good alignment. By the time you reach layer 11, there is very, very good alignment. So just look at the last 3 words and just look at pedestrian to understand how the model is learning to align the word embedding and specific image embedding. How is correlation calculated? You can simply take the dot product. That is one way to calculate correlation. We will look at that in today's lecture. Okay, so that is how you basically construct a similarity score between vector embeddings corresponding to text and vector embeddings corresponding to image. I anyway plan to conduct a full-blown research paper review separately for this particular paper, but I just wanted to show you this because this is so beautiful. Okay, so in traditional AI, we know we have discussed this text input converted to text output, LLM, next word prediction. Vision transformer was image input converted to class. Basically, you were using it for classification. In the last lecture, we did MNIST classification. VLM can ideally do both. It can take multi-model input, and this is useful for very many different tasks. If you show an image and ask a VLM, what is the person in this image doing? It's called VQA, visual question answering, or visual common sense reasoning, or image captioning. So all of this vision language model can do. In today's lecture, what we will be doing will be an image. We'll take an image and the corresponding captions, and we will see how to construct alignment between the caption embedding and the image embedding. And there are actually many, many different types of VLMs you can construct. Okay, unlike when you say vision transformer, you primarily think about the vision transformer paper, the one produced by Google. But when you say VLM, there are actually many papers that propose many different models of vision language model. It's not like just one thing. But as long as that model allows you to produce this thing like a joint embedding. So in this joint embedding space, what is done is the image, which is like this, and the caption. Let's say caption is happy dog running towards the camera. So this caption is actually, we know as a human, we know that this caption is aligning very well with this image, right? Then ideally, the vector embedding corresponding to this caption, this image, and vector embedding corresponding to this caption, they should be very close to each other. So here I'm just showing the tip of the vector. I'm not showing the vector line, but basically the vectors should align very much. So this joint embedding or joint representation space, and in that there should be very good alignment between image and text. That is the goal of a VLM, vision language model. Now we will come to the idea of NanoVLM. So while building this VLM, you will understand what exactly the architecture of VLM looks like. So there are a few questions. Basically, we can create VLM based on regions instead of patches. Exactly. So VLM, typically we don't feed patch into a VLM. We can do that. I mean, in vision transformer, it's anyway patches, and each patch, depending on the patch size, will only enclose a few number of objects. So yes, it is possible. Now most of your questions will be answered in this section when we build it from scratch, because here we will discuss what the data set look like, what kind of task our VLM is going to do, what the exact model architecture is in encoder for both image and text, and what's the loss function. So let us discuss this. So the task for which we are going to build the NanoVLM, and by the way, one more thing is, we are naming this as NanoVLM because of a very specific reason. The number of parameters here will be less than 1 million or close to 1 million. So if you look at, let's say, a small language model, it will have around a billion-ish parameters. But nano models, I mean, it's up to you. Like, you can name, I mean, if something has, let's say, 100,000 parameters only instead of 1 million, you could maybe call it as some other VLM, and you can say it's a nice VLM that you propose. So it's up to you. But here, when I say NanoVLM, I mean a vision language model with just less than 1 million parameters total. Total number of trainable parameters should be less than 1 million. We will also, at the end of today's lecture, we'll hand calculate the total number of parameters to conclude that indeed our VLM has only less than 1 million. We'll calculate the exact number of parameters. Okay, so now the task description. What are we going to do today? So task description is, we will try to build a data set with images and corresponding captions. So we are going to build a synthetic data set today, and the task will be, if I input on the trained VLM, if I input a new caption from the validation data set, the VLM should be able to tell me which image is the most correlated image corresponding to this caption. So that is one type of task. So finding the most appropriate image from the validation image data set for any given caption in the validation data. The opposite task is, given an input image from the validation data set, the VLM should be able to propose, this is the best caption that describes this image from the data set. So these are the two tasks. Both are kind of symmetrical. So on one case, you want to find the best image corresponding to your caption. In the other case, you want to find the best caption corresponding to your image. Now, here is a very specific word, NanoVLM, a tiny clip-style model trained on synthetic colored caption. I'll come to what is the synthetic colored shaped captions, but what is this clip-style model? So CLIP was a paper proposed by OpenAI. It is very famous. This is the paper. So this paper did not introduce the idea of contrastive learning for the first time. I'll tell you what contrastive learning is, but this paper utilized the idea of contrastive learning for teaching a vision language model to learn from text and image. And if you look at the authors, the last author you might recognize, Ilya Sutskever, one of the former co-founders of OpenAI. This paper has very high citations, around what, 60,000 or something like this. Yeah, 46,000. So very high citations this paper has. So some of the famous papers from vision language models, I recommend you to read if you want to read. One is CLIP paper. CLIP paper is actually very nicely written. It's very simple language, but it's a bit long. It's 48 pages. So before you start with CLIP, I recommend you to read Visual Bird paper. This is a relatively short paper, I think 12 or 15 or something like that number of pages. And its language is very, very easy to understand. So this is one paper which you should definitely read. Another paper is Wilbert. Wilbert has slightly more number of citations, around 5,000. He's cited by around 5,000 people. Wilbert was produced just before Visual Bird was proposed. And in my paper reading workshop, I do plan to cover all these three. CLIP will be the most difficult one simply because of its length. But Wilbert and Visual Bird, I'm hoping to be easy. So I recommend you to just read this quickly. It's not especially Wilbert and Visual Bird, they are very easy to understand. One more paper, I'm sorry to recommend so many papers. One more paper I highly recommend you to read, if you have the time, is the Bird paper, original Bird paper, which came right after, I think in 2019. Has very high number of citations, 150K. So Bird paper is also not that long. It's very, very nicely written. The language of writing is relatively easy to understand. So the order in which you can probably read, if you have the time and bandwidth, is you can first go through the Bird paper, and then you can look at maybe not Wilbert, go through Visual Bird, and then go through Wilbert, and then go through CLIP. So these four papers, I can put the link here. So first you can go through, where is this? Yeah, this one is Bird. So go through this first. Then second, go through not Wilbert, Visual Bird, because Visual Bird, in my opinion, is a slightly simpler architecture compared to Wilbert. In Wilbert, you will see the idea of cross attention between query from image and key and value from text. So here in this image, what they are showing is, so they had two streams, one stream for image and one stream for text. So usually for producing attention weights, we take query, key and value, everything from the same data set, right? But here what they did was query they took from the image and key and value they took from the text for here. And similarly for the text stream, query they took from the text and key and value they took from the image. So that is how they constructed this co-attentional transformer layer, this co-TRM. So it's like a very, very good idea. And last, fourth, you can read the CLIP paper. CLIP is actually written in a very nice, easy to understand language. Only thing is it's a little bit lengthy. Other than that, I don't have any issue. But in CLIP, they use this idea of contrastive learning. This is another paper. I don't think you need to learn contrastive learning. I mean, from the paper, it's not really necessary, but I'm just showing you this paper just in case if anyone is interested. So this contrastive learning of visual representation, what they introduced was, actually, let me explain it through Miro board. That'll be better. So what they did was, let's say you have bunch of images, okay? You have 1, 2, 3, etc. N different images of a dog, of a mug, of water bottle, microphone, pen, whatever, bunch of images. And let's say you have captions that describe those images. So these are now the corresponding captions. So this is image number 1. This is caption number 1. Then image number 2, caption number 2. So the image and caption ideally should align very much. Now, the way they constructed this data set, one smart way to do this is, for website, the images have alt tag, right? So image, if the website is not loading or something, you will see the alt tag. In Instagram, you might have seen it sometimes. So by scraping the internet data for images and corresponding alt tags, you can get a huge data set where image and corresponding captions are there. Many times captions may not align, but if the data set is very good, captions align really well. Now, what is done is, in contrastive learning, the idea is you pass the individual item. So you have n data points, okay? You pass each of these separately through text encoder to produce vector number 1. So this is a vector number 1 corresponding to first text caption, vector corresponding to second caption, third caption, and nth caption. These are not, this is not an n-dimensional vector. Please don't get confused. These are n vectors corresponding to the n captions. Actually, this should be capital N. Now, similarly, you pass this through an image encoder. This can be vision transformer or CNN to produce n vectors corresponding to images, image 1, image 2, image 3, etc. up to image n. Now, we know that corresponding to image 1, caption 1 is the aligning caption, right? Because image 1 is that of this puppy, caption 1 is Pepper the Aussie pup. So this image 1 aligns with caption 1. However, image 1 should not align with caption 2. Image 1 should not align with caption 3 or with caption n, right? So if you look at this from the dot product perspective, I1.T1 should be high, but I1.T2, I1.T3, all of these should be low, ideally. So this should be ideally close to 1. These numbers should be ideally close to 0, correct? Now look at it from the captions perspective. So this was from the image perspective, this particular row. But look at it from the captions perspective. Caption number 1 should align with image number 1. But caption number 1 should not align with image number 2. It should not align with image number 3 or n. Which means if you look at this column, the I1.T1 should be high, close to 1 ideally. But T1, when you take dot product with I2 or I3 or IN, it should all be ideally close to 0. And by the same logic, I1.T1 should be highest, I2.T2 should be high, I3.33, like this. This whole diagonal should be very, very big numbers. I mean, very big meaning as close to 1 as possible when you take dot product. Rest of the numbers should be 0. So this is called contrastive learning. Why is it called contrastive? Because these are called positive pairs. I1 and T1 are positive pairs. Those are pairs of images and text. So image and corresponding caption that are aligning. I1 and T2 are negative, I1 and T3 are negative, I1 and Tn are negative. Similarly, T1 and I2 are negative, T1 and I3 are negative, T1 and In are negative. So this is the idea of contrastive learning. So I1 and T1 should be aligned because in our ground truth data, image number 1 and caption number 1, they are the corresponding image caption pairs because we need a data set pair. We need image and corresponding caption like that large number of data set. N is not the batch size. Yeah, oh, sure, N can be batch size, but here N simply means you have N data points. You have N captions and N images. Now, one question you may have is, what if I have similar, what if let's say images that of a, so here it's a puppy. What if I have one more image of a puppy? Then maybe caption T1 will align with that, right? So ideally, when you construct the data, that is one shortcoming with this contrastive learning. So here we try to push I1 and T1 as close to each other as possible and try to push away everything else. T1 and I2 should be pushed away. T1 and I3 should be pushed away. So that is one side, I would say, one negative aspect about contrastive learning is that if there are two images that are similar, or if there are two captions that are similar, then the model is a little bit rigid. Model will not try to align those, the image and the similar caption. Model will look at the exact caption. But the good thing in clip paper was, in clip paper, they used 400 million data points from the internet. Somewhere in the paper, they are mentioning that 400. Yeah, see, so they used 400 million image text pairs. And just because of the sheer volume of the data, this shortcoming of contrastive learning was not an issue. It won't be an issue for us also. I will show you why when we construct the data. And correlation is simply calculated by taking dot product between two vectors. I1 is a vector, T1 is a vector of same space. So I1 dot T1 will be like the dot product. And what is the goal here? The goal is, if I go back to this image, the goal is to push these two vectors as close to each other as possible. But this and this should be farthest away as possible. This and this should be far away. This and this should be far away. Similarly, this and this should be far away, this and this should be far away, this and this should be far away, because these are all negative pairs. But in this particular example, these two are positive pairs, but this is a negative pair. This is a negative pair. All other green-red pairs are negative, but these two are positive. So the goal is to align positive pairs and push the negative pairs as far away as possible. Now, let us look at how to construct, how will the loss look like? So let's say I have one image number I, okay. Now I have n captions to compare this against. So caption is T for text, T1, T2, T3, etc. Right? So ideally, image number I should match really well with text number I. And image number I should not match really well with any other text, because I should have high cosine similarity with Ti, but I should have very low cosine similarity with all other T's. So one way to construct like a probability distribution, if we were to take dot product of I1 with T1, I with T1, I with T2, etc., this dot product will be probably close to 0, but let's say 0.1, this may be 0.1, this may be 0.2, and this may be 0.9, and the last one might be 0. something 2. But this should be the highest number. I and Ti should have the highest dot product. Now, how do we convert these set of numbers into a probability distribution? I have now a set of numbers. How do I convert numbers to a probability distribution? I simply take softmax, right? So what I can do is e raised to I Ti divided by sigma e raised to I Tj, where j runs from 1 to n. So now this is the softmax score corresponding to the matching positive pairs. Now let's do one thing. I have a small Excel sheet which shows the softmax number. So this is just an example. Let's say I have now 3 similarity scores between, let's say, this is, let's say, Ti, this is some other pair, this is another pair. So consider that these two are negative pairs, this highlighted blue ones. This is a positive pair, and these are the similarity scores, which is the dot product between the vectors, two pair of vectors. Now I can take softmax of this, and when I plot it in softmax, look at what has happened to my softmax. So this is the original distribution, 0.1, 0.2, 0.8. But when I took softmax, the softmax actually became less sharp. You see, softmax distribution became more even. But usually we don't like this, because this even, that's not the point of taking softmax. We don't want this even distribution. We want sharper distribution. We want the model to be able to say, yes, with very high likelihood, the third item is the positive pair. First and second items are negative pairs. So then what can I do? I can simply mathematically, if I divide, let's say, I and Ti by number like 0.1, will my softmax become more sharp or less sharp? More or less? it will become more sharp because the value inside the exponent is now increasing. So, and that's because this number is less than 1. But if this number was 10 instead of 0.1, it will become less sharp, right? So this parameter is called temperature. So we can denote it by some tau or T or something. Ti divided by tau by sigma j equal to 1 to n e raised to ii tj divided by tau. Okay, so now this is the temperature value, which is called as temperature, but essentially it's a parameter that we introduce whose value can be like between 0.01 till 0.2. I mean, these are thumb rules. There is no specific rule. It should be generally less than 1 for it to work. So we'll introduce this also. So this can give you a very sharp softmax distribution. So here the third plot in the Excel sheet, I have introduced a temperature parameter of 0.01. And you can see that now the softmax is very sharp. These two are negligibly small. It's not even visible because those values are like close to very close to 0 when you take the softmax of the three numbers, because my temperature is very small. But if the temperature is like 0.2 or something, see, the sharpness has reduced, but still it is reasonably sharp, right? So this is the reason why there will be one temperature parameter in the loss. Now let's think of one more thing. So this was the case where I was trying to be mapped with T1, T2, etc. up to Ti. But same thing can be said for Ti also. Ti, if I look at it, this has I1, this can be compared against I2, this can be compared against II, and so on. So I can construct a symmetric version of the same thing by saying, so this is, let's say, the loss, not loss, similarity, softmax similarity score or probability distribution when you are looking from I image to text. But I can construct something like same thing for text to image, softmax text to image. The only thing that I have to do here is e raised to Ti II by tau divided by sigma j equal to 1 to n e raised to Ti ij divided by tau. So it's just that in the denominator, the instead of Tj, it will be Ij. That's it. So you are iterating through all the n images instead of all the n texts. But that's not it. Like this, how many Ti do I have? I have n number of Ti's, correct? I have n, I have T1, I have T2, T3. So I can compare T1 with all possible images. I can compare T2 with all possible images. I can compare Tn with all possible images. Similarly, I can compare I1 with all possible texts. I can compare I2 with all possible text, and I can compare I3, In with all possible texts. So now, if I want to have a loss, how can I convert, by the way, a probability distribution into a loss? Because here, higher the probability, the loss should be lower, right? If my softmax probability score for the positives are high, I should have a low loss. What should I take? Just taking logarithm is enough, negative log, right? Because if my numbers are between 0 and 1, and for positive pairs, let's say my score is 0.99, softmax score is 0.99. And then if it is 0.99, we should take a negative log, because negative logarithm of 1 is 0. Negative logarithm of a small positive number will be a very high positive number, because log 0 is minus infinity. This tends to be minus infinity. Log of 1 tends to be 0, which means if I take negative of this, negative logarithm of a small number, let's say 0.001, will be a big number, a big positive number. Negative logarithm of, let's say, 0.999 will be a very small positive number. Let's say this is 0.00, something like this. This is, let's say, 99. I'm just writing a random number, okay? But I hope you get the point. So what we have to do is we have to take the negative log of softmax. So negative log of this guy. This I can call as similarity score between II and Ti. This. So negative log of e raised to II Ti divided by tau by sigma j equal to 1 to n e raised to II j, not jj, tj, text j by tau. So this is for image to text, and like this we'll have text to image, but then I have to do one more thing. I should loop it through all possible images because I have n number of images. So I can simply say sigma where I goes from 1 to n and then minus 1 by n. So this is now a mean. So I hope you are following me. What we are simply doing is I have n images and n captions, correct? Every single image can be compared to every single captions. Similarly, every single caption can be compared to every single image. If I am comparing ith image with all captions, the loss will be negative logarithm of e raised to image number I compared with positive pair divided by, this should be t, positive text pair t from, and then j equal to 1 to n e raised to II t j by tau by tau. This is for just for the ith image. Like that, I have to do for all images. So I simply do minus sigma I equal to 1 to n, 1 by n. So minus 1 by n times this, right? So this is basically now the loss function L, loss function I to t, image to text loss. Like that, I can construct same opposite version like L for t to I, text to I. And then I can add these two losses and take an average, half. So then basically the loss, contrastive loss or clip loss, I should rather say, clip loss equal to 1 by 2 times Li to t plus Lt to I. This is basically the clip loss. This is also called symmetric loss, and you simply take an average. You can or cannot take average. It's up to you because ultimately at the end of the day, you just care about having a loss that is based on the contrastive pairs and positive pairs. All right. So this is the clip loss, and I will show you the formula which you may have seen before. But this is the Li to t exponent of xi. So now x is image, y is text. So xi t yi is basically transpose. So in vectors, you take transpose, A transpose multiplied by B is how you take dot product between A and B. So that's why you see this T here, transpose, divided by sigma. So here sigma is the temperature, sigma is the temperature. And this sigma I equal to 1 to n is because you are iterating over all the images. And then negative logarithm because you want to convert softmax into a loss score. Softmax because you want to convert the dot product similarity scores into a probability distribution. So think about all the things which we did. We first said similarity is equal to dot product. Then we said to convert dot product to probability distribution, we need softmax. Then we said to convert softmax to loss, we need negative logarithm. Then we said we have to take this not just for the ith image, we have to do it for all. So we just did sigma I equal to 1 to n, 1 by n. Then we said we need symmetry. We need to do the same thing for text. So basically, we do the same where image and text are swapped. Loss have twice the diagonal dot product. Yes, so diagonal dot product will be occurring twice, but the remaining ones will not occur twice. That's correct. Because let me go back to this image. If I delete all of these annotations, in image to text loss, you are considering all these items, right? And text to image loss, we are considering all these items. So if you now look at this I1 dot T1, the positive pair, it is getting counted twice in the loss function. So that is true. In this formula, we have taken softmax, this exponent, this is the softmax. Why? What does this mean intuitively? Intuitively, it means you want image number 1 to align with text number 1 if you compare with all the possible text captions. Similarly, text number 1 should align with image number 1 if you consider all the possible images, right? Because sometimes you may want to search a good caption for a given image, or sometimes you may want to search for a good image for a given caption. I'll give you an example. Let's say you ask, let's say you want to do an image search. You have a database of a bunch of images, and you are running a jewelry shop. And in your jewelry shop, you have a bunch of jewels which have names. And now I come to you and I say, I need something that looks really good for a diamond square cut ring, something like that. Then that is the caption that I'm providing you. And from your database, you should find the best possible image for that caption. In another case, I may come to you and say, hey, here is my ring. Here is the image of my ring. What is the name of this actually, according to you? And then maybe you want to tell, I mean, it's a made up example, but I hope the example makes it clear why you need image map to text and text map to image. But this is the loss function that we'll be using. Anyway, I'm coming to explain the loss function in detail. I was coming to explain this in detail later, but I already explained it. Now, what is our data set? This is very interesting. So first of all, I wanted a simple data set, because if I use some big data set from Kaggle or somewhere else, it will take forever me to train. So what I thought was, I will create a data set synthetically, image caption pairs. Now, what my data set looks like is I have different colored objects. So I have 9 different colors, red, green, blue, etc. Then 3 different shapes, square, circle, triangle. Then 9 different positions where this shape can occupy the image. So center, left, right, top, bottom, then top left, top right, bottom left, bottom right. So totally, now I'll have 9 times 9, 81, 81 times 3, 243 images, right? And captions that I'm constructing will look like this. So these are now the synthetic images that I created. So this is pink circle top, because this is like a circle. It's a low resolution image, which is why it does not look like a circle strictly, but it's a circle of pink color. It's at the top of the image. Center is somewhere here. That's why, although it does not look like top, it is top. Now, second image is brown circle occupying bottom right. So these are different images I plotted as a grid, okay? Just don't get confused since there is no boundary. So this is one image, this is another image. So this is now the caption, this is the corresponding image. This is the caption, this is the corresponding image. So this can be constructed programmatically. So I will share the code with you today so that you can also create it synthetically just by running the code. So totally you will have 243 unique image caption pairs. Now, what's the difference between this and, let's say, a bunch of images with labels as cat or dog? What's the difference between those two? Here you have 243 images and a bunch of labels. In a classification task also, you have a bunch of images and they have labels. So what's the difference between this and that? Complex caption. The main difference is that here you don't have repeating labels, right? Because every image is unique and every caption is unique. So can you technically train just a CNN classifier here? You can't, because you don't have multiple images belonging to the same label, right? If you were to call the caption as a label, you have 243 images and 243 labels. So it will now become a 243 class classification with just one image per class. Can you build a classifier? No. So there is very much difference between the thinking of these captions as labels. This is not labels, okay? But labels for a image classification between cat and dog will be, you will have bunch of images that are cats, bunch of images that are dogs, and captions or labels of every single one of those dogs will be just dogs. Caption or label for every single one of the cat will be cat. So corresponding to cat label, you will have bunch of images. Corresponding to dog, you will have bunch of images. Here, that is not the case. So this is not a multi-class classification problem at all. So please don't get confused. Then what we do is, we have 243 images in the data set, which we will split into training and validation. So 80% for training, 20% for validation. So it will be a very small data set, and let's see how well we can train this. Then I want to go through the overall model architecture. So overall model architecture looks something like this. So what are the negative images? Negative images are simply the wrong captions. The correct caption pair, image pair. So let's say I take this image. This is brown circle at the bottom right. So this brown circle bottom right caption and this image will form positive pair. But this image and all other captions will form negative pairs. This caption and all other images will form negative pairs. So now what our model architecture for today will look like is we will build, so today we will not be using vision transformer. We want the training to be a bit faster. So we will use CNN based encoder for constructing vector representation of these images. So by the time it reaches here, the image reaches here, it would look like a vector of let's say 64 dimensions or something. And this text we will convert into encoded version, basically another 64 dimensional vector. And now you can compare all these 64 dimensional vectors with these 64 dimensional vectors using clip-like contrastive laws, the same formula which you saw, exponent of dot product divided by sigma exponent of dot product. So now this is the vision part of the VLM, and this is the text part or language part of the VLM. And what will happen is if this VLM is not trained very well, this vector and this vector will not at all be correlated. I will actually show you one image, which anyway you will get at the end. So look at this. So this is a 64 dimensional embedding of my vectors. So this is before training and this is after training. Okay. And look at the correlation. So dot product between, so now I just use the color map for showing 64 dimensional vector. Otherwise I can't display it. Now this color map correspond to the numbers, and you can see that there is very little. So if you compare dimension 1 of the text and dimension 1 of the image, it's not comparable. This and this not comparable. This and this not really comparable. So overall, when you look at the pre-trained image embedding and pre-trained training text embedding, they are not very similar. And because of that, the dot product here is very low, 0.0369. But after training, you look at the similarity. They are not looking exact, but there is a lot of similarity. Like this and this look similar, this and this look kind of similar, this and this look kind of similar, this and this look kind of similar, then this and this look kind of similar. So the similarity is much higher, and the similarity score is 0.8873 in this case. So this is what we are trying to do. What we are trying to do is we are trying to align the image embedding and text embedding through clip loss. So we will train the image encoder and text encoder so that the alignment can become better and better and better after training. What do we mean by better? The dot product between two positive pairs should be very high. Here is another example where I, instead of taking 64 dimensional embedding, I took 3D embeddings. 3D embeddings we can try today. And this was the embedding, how the embedding was looking. I don't have the cosine similarity score here, but this is how it was looking before training. They were, and these were for two positive pairs. So for same image and caption. So this was one image and this was the corresponding caption. They were having no alignment. They were pointing in kind of different direction. And after training, you see, they have very good alignment. They both are kind of pointing in similar direction in the three-dimensional space. So this is what happens when you train the VLM to produce better and better embeddings through clip loss. So this is our goal today. We want to build something that can do this. Okay, so now let's come back. Okay, this we discussed. Now let's look at the image encoder separately. So image encoder, what we are going to build today is a CNN. We can use vision transformer and use the last, the zeroth CLS token, class token for the as the final embedding. But let's keep it simple. Let's use a CNN. Now I'll show you how the CNN architecture look like so that you all understand what happens to the image as it passes through different layers. So the image resolution is very small. It's 32 by 32 image. So it will be looking very pixelated, but it will have RGB channels, 3 channels. So input image will have 32 by 32 by 3. Then what happens in the next layer is by the time image reaches the next layer through convolution, it will become spatial dimension will shrink to 16 by 16 and number of channels will expand to 32. Now this we had discussed in detail in the last lecture, but I want to refresh our memory. Tell me for this to happen, let's say I am using a 3 by 3 kernel, okay, 3 by 3 convolution filter. what should be the padding and what should be the stride? Padding equal to what? Stride equal to what? If I want to get this kind of an output. My kernel size is 3 by 3. So kernel size is 3. Okay. Padding equal to 0, stride equal to 2. Padding just stride equal to 2. For those of you who think stride should be 2, why should it be 2? What's the logic behind stride equal to 2? The logic is that when you are taking, instead of stride equal to 1, if you take 2 pixel jumps at a time, the width dimension will get reduced by half. Height dimension will also get reduced by half. And that is what is happening. 32 is becoming 16, 32 is becoming 16. So stride should obviously be 2. But padding, what should it be? Padding, should it be 0 or should it be 1 or something else? There must always be padding. See, think about this. If stride is equal to 1, okay, padding equal to 0, will the dimension remain or will the dimension shrink? It will shrink by 2 along the width and 2 along the height. So you have to have one padding of 1 pixel along the top, along the bottom, along the right, and along the left, which means there has to be a padding if you don't want dimensionality loss if stride was 1. So here 32, to preserve 32 as 32, you should keep stride equal to 1 and padding equal to 1. If stride was 1 and padding was 0, 32 will become 30, right? Because you are losing 1 pixels, 1 row on the right, 1 on the left, 1 on the top, and 1 on the bottom. Now tell me, how many channels should my filter have? Number of channels for my filter. Is it 3 or is it 32? My question is number of channels for my filter. The answer is 3, because this, you should never forget this diagram. Actually, let me show you here. This is my image and my filter acts like this. Like this, like this, like this, like this. So never forget this. This is how the filter acts. So whatever is the number of my input, okay, whatever is the number of channels in my input, same number of channels should be there in the filter. What should be the number of filters in this convolution? What should be the number of filters? There should be 32 filters, because filter number 1 should produce this output. Filter number 2 will produce this. Filter number 3 will produce this. Filter number 32 will produce this. Okay, so I have 3 channel filter of kernel size 3 by 3 of and like that I have 32 filters. Now tell me, how many learnable parameters does this make? If I have one kernel with 3 by 3, how many learnable parameters are that? This 3 by 3 kernel means number of parameters is 3 multiplied by 3, 9 parameters, right? But then I have how many such channels? How many 3 by 3 kernel channels do I have in the input? I have 3 of them. But like this, I have 32 filters, correct? So these many learnable parameters will be there, but there will be one more set of learnable parameters. There will be one bias parameter per output channel. So how many output channels are there? 32 output channels are there. And if there is one bias along each output channel, I'll have another 32 added here. So total number of learnable parameters, okay, when you go from here to here, will be whatever this number is, 3 times 3 times 3 times 32 plus 32. Why is this 32 coming? What is this 32? It's the 32 filters. What is this 3 by 3? It's the kernel size. What is this 3? It's the number of channels. What is this 32? It's the number of bias parameters, because you have 32 filters. Each filter has one bias term. Now, next is simple. From here to here, how many channels should be there at the input? you go from here to here, spatial dimension is shrinking from 16 to 8. How many channels should be there at the input? It should be 32. Number of channels at the input is equal to number of channels, number of channels in the filter is equal to number of channels at the input. So the filter should have 32 channels. Kernel and kernel padding stride, they will remain the same because 16 is becoming 8. So kernel will be 3 by 3, padding will be 1, stride should be 2. Then number of filters should be how many? 64, because output channel, there are totally 64 channels in the output. So now how many learnable parameters will that be? I have a 3 by 3 filter, but this filter has 32 channels. Like that, I have 64 filters, and for each filter, I need a bias. So these many learnable parameters will be there. Now, same logic applies from here to here. 64 becomes 128, 8 by 8 becomes 4 by 4, 128 becomes 256, 4 by 4 becomes, 64 becomes 120, and then 4 by 4 becomes 2 by 2, 2 by 2 becomes 1 by 1. But the 1 by 1 logic is different. I will tell you what is happening. So you have actually 4 convolution. This is convolution number 1, number 2, 3, and 4. All of this, we are using kernel size 3 by 3. Padding is 1, stride is 2. So 32 becomes 64 means 2 filters. No, 32 becomes 64 means, so I'll show you once more. Here, let's say dimension is 10 by 10 and channels are 3. And if I want to produce 6 channels at the output, okay? If I want the output to be something like this, let's say 5 by 5 and 6 channels, what should be my filter dimension? If filter kernel is 3 by 3, let's say each of these are 3 by 3, I should have 3 channels because input has 3 channels. I should have padding equal to 1 and stride equal to 2. Stride equal to 2 because 10 is becoming 5. 10 is divided by half. But since I have 6 channels at the output, I should have 6 filters. So first filter will go like this and produce. So first filter will do that to produce whatever numbers are present in this. Second filter is responsible for, so this is the second filter with 3 channels. It is responsible for this. Sixth filter is responsible for this. Now, if I had 64 channels, I will need 64 filters. If this number was 32, each of these filter will have 32 channels. So that is exactly what is happening here. When you go from 32 to 64, your input number of channels is 32. Your output number of channels is 64, which means number of filters should be 64. Each filter should have 32 channels. Okay. Okay, so we have 4 convolution operations. But following this, we do something called global average pooling, GAP. I will show you how to implement this, but basically you have 4 numbers here, right? 2 by 2 means you will have 4 pixel values. You will take an average of those 4 numbers just to produce one number. And number of channels actually is not changing. This 128 is over here. Okay, don't get confused. So this is 128. This is 256. And global average pooling does not change the channel dimension. 256 will remain 256. But this is global average pooling. Okay, it just averages these 4 numbers to one single number. And then now you have a 256 dimensional vector. But if your input dimensionality is, let's say, 64 input embedding, let's say your embedding space has to be 64. How do you go from a 256 dimensional vector to a 64 dimensional vector? What would you use? You will simply use, you can use some feed-forward neural network multi-layer perceptron, but basically a matrix multiplication, right? And how many trainable parameters will this be? Okay, before that, how many trainable parameters are this? Global average pooling. Who says it is 4 times 256 or something? Global average pooling number of parameters should be 0 because you don't need any trainable parameters to take an average of 4 numbers. It's simply those numbers summed up divided by 4. So global average pooling or max pooling, those operations does not introduce any additional parameters. Now let's think about how many parameters you have when you go from 256 dimensional vector to 64 dimensional vector. How many trainable parameters? 256 times 64. And how many bias terms? 64, because each dimension at the output can have one bias added to it. So these many number of trainable parameters. And then you do layer normalization, plus you convert, after layer normalization, you convert it into a unit vector, the magnitude to be unit vector, so that when you take cosine similarity, maximum possible value will be 1, minimum possible value will be 0. Okay, so then what else? Yeah, one more question. In layer normalization, what exactly are we doing? Layer normalization does this. If xi, this is the input, ith input, and here let's say it is x1, x2, etc. up to xn. Okay, first thing is I'll take the mean of this, which is mu, standard deviation of this, which is sigma. Then I will say xi equal to xi minus mu divided by sigma. This is one step. Now, are mu and sigma learnable parameters here? So first of all, by doing this, if I do this, the new set of xi, what will be the new mean and new standard deviation? What would this be? Mean should be 0. Standard deviation will become 1. But are mu and sigma learnable parameters or not? They are not. They are not learnable parameters. Those numbers are byproduct of just mathematical calculation on these numbers. Now, what you have to do is something called scaling and shifting. So essentially, what happens to xi is xi minus mu divided by sigma multiplied by beta I plus gamma I. Beta and gamma, I don't know what the terms are in literature. You can call beta, gamma, delta, whatever. But essentially, you do a scaling and you do like a bias term. So you will have two terms. These are now learnable parameters. You will have two terms associated with each dimension. X1 will introduce one beta and one gamma. X2 will introduce one beta and one gamma. Xn will introduce one beta and one gamma. So by that logic, now how many learnable parameters will your layer normalization introduce here? It will be, how many of you think it should be 2? If you say 2, why is it 2? I have a 64 dimensional vector. For each dimension, I need a scaling factor. I need one beta and one gamma. So total number of learnable parameters in the layer normalization will be 2 times 64. So 128. Now we can calculate currently, but maybe let's push it to the end of the lecture. So by the same logic, now we can calculate how many trainable parameters my image encoder has, right? And like that, I can do for text encoder to calculate the total number of trainable parameters. And that will be the definition of whether my model is nano or micro or whatever. So that we can do at the end, but now you know the logic. Now let's move on to text encoder. Text encoder is actually much simpler. So the use of gap step is, so gap is you ultimately want just like, one number in each dimension because you want a vector. Now, how do you convert a 2 by 2 into 1 by 1? Either you can take a mean, or you can simply take something like a padding 1 stride equal to 2, 3 by 3 convolution. That also is fine. But the problem is if you do that, you will have more number of learnable parameters. If you simply do global average pooling, it does not introduce any parameters. You can do average, you can do max, anything is fine. Because this is anyway experimental. I only made up this architecture, so it works very, very nicely. So I decided to keep it. We can try max pooling also instead of average pooling. But now answer one question. In which, so if I have convolution 1, 2, 3, 4, in which of these convolutions do I have the maximum number of trainable parameters? Is it in 1 or is it in 4? It should be here, because here the number of learnable parameters will be something like 64 times 3 times 3 times 128 plus 128, something like that, right? So the more the number of channels here you have, the higher the, I mean, it's not a general rule, but in general, in this case, fourth convolution operation will introduce the most number of learnable parameters. So if you had a convolution operation here also, it would have introduced again even more number of learnable parameters. So ideally, you want to reduce the further convolution operations. If you want the model architecture to be small, I could have introduced a 2D convolution here also, but then I can do the calculation. But my guess is learnable parameters. Then if I had a convolution here also, this guy will have the highest number of learnable parameters. Then maybe my model will not be nano anymore if I want less than 1 million parameters. We'll see that. Okay, now in text encoder, the interesting thing is I had experimented with two types of text encoders, one with attention, multi-guide attention, and one without multi-guide attention. So text encoder part is very, very simple. First, let us think about our dictionary. Okay, let me go back to our captions. Look at the caption: pink circle top, blue circle top. So the captions are created based on the color, space, shapes, space, position, correct? So in my vocabulary, that way, how many unique tokens will be there according to this logic? What will be my vocabulary size? For those of you who are saying it is 21, what is the logic? Those of you who said 21, they are correct. Actually, it's not 21, it's 22, but the logic behind 21 is correct. See, vocabulary is basically tokens. This is not a token. This is a sentence. When I tokenize this, I will take only the words. So totally in my dictionary, blue will be there. So if I consider this sequence and this sequence, number of unique tokens are not 6. Number of unique tokens are pink, circle, blue, and top. It's only 4. So the total number of tokens will be this. This will introduce 9 tokens. This will introduce 3 tokens. This will introduce 9. Plus, I can have a classification token also, CLS token also, just like how we did in the last lecture. So total CLS token plus or class token plus these 9 tokens, these 21 tokens, my dictionary will be totally of just 22 tokens. That's it. Right? Now, that is let's come back to the text embedding. So now I need some sort of way to convert 22 tokens into 64 dimensional vectors, correct? Because each token is now 64 dimensional. And what kind of matrix can I use for this? What kind of matrix can help me convert a vocabulary in which there are 22 items into 64 dimensional vector, any given one? I can use an embedding basically. I can use an embedding whose dimensionality will be something like, let's say 22 by 64 or something like that. Basically into the embedding, into the vector embedding function, I will have to pass the 22 and I will have to also pass 64. 64 is the embedding dimension of each vector. 22 is the number of vectors or number of tokens in my dictionary, in my vocabulary. So we will need that. Then how did we usually construct context vector? My context vectors were softmax of key times or query times key transpose divided by square root of dimensionality of the key space multiplied by value, correct? This was my context vectors. And what was this? This was attention weighted average, or let's call it as maybe attention weighted sum. Both are fine because those weights are anyway less than 1. But basically, we are taking attention weighted sum of what? Context vectors are equal to attention weighted sum of dash. Context vectors are equal to attention weighted sum of dash. Value vectors, because these are attention weights. And I'm taking a attention weighted sum of value vectors to get context vectors. In the simplified attention, what we did was we took softmax of x dot x transpose multiplied by x itself. We did not use query key value. in a simplified sense, we can choose not to have query key value also, which means no attention is needed. We simply take the dot product. So one thing which we can do is a very simple thing is, let's say my token is blue square top. Now I have to convert this into, and then I should have a CLS token also. And in my dictionary, CLS token may have index 0, blue may have an index of 5, square may have an index of 3. I'm just putting random numbers here. Top, let's say it has an index of 17, something like this. Now, what I can do is, and then these indices will now be converted to 64-dimensional vectors, correct? Each of these are now 64-dimensional vectors. If I had a multi-head attention over here, MHA, these would have become context vectors, correct? This will be 64-dimensional context vector. This will become 64-dimensional context vector. This will be. And then what I could do is I could simply take just like how we did in vision transformer, I could simply take the classification tokens representation, whatever this guy is. And I can compare now this with what? What will I compare this with? 64-dimensional embedding of my image, right? So then I can compare this with 64-dimensional embedding of the image. This is if I have multi-head attention. If I don't have multi-head attention, a simple thing which, this is just a trick. It happened to work because my data set is so small. What I did was I just took an average of these. So I added these 4 things up, no attention. I just added these and divided by 4 and said that is now my final context vector. Although it is a weak context vector, it's a 64-dimensional context vector. Then I can simply compare that with the 64-dimensional vector, which is corresponding to image. So we can try both. In one case, we can use multi-head attention. In another case, we'll use no multi-head attention, just simple averaging. In both cases, I'll show you how it works. Text encoder is that, but code we'll come to in a bit. Loss function, you guys already know what the loss function is. Loss function is simply the same symmetric clip-like contrastive loss. What else is there? That's it. I think now we are ready to go. Let's start coding. Loss alone, should I explain? Okay, so loss is basically, I have now my images circle, blue, red circle top. So I have a bunch of images which are looking like this, and I have captions. So captions, let's call it as XI. Images, I call it as YI. Now my L to Li to T, image to text, is equal to -1 by n, sigma I equal to 1 to n. Then exponent of Xi transpose multiplied by Yi divided by tau, tau is the temperature, divided by sigma j equal to 1 to n, Xi Yj, exponent of Xi Yj by tau. This is Li to T, Lt to I. So here we are taking, first we are taking the dot product for similarity. Oh, I forgot to put the logarithm, log of this. Then we are taking this exponent. What is this? What is this guy? Inside the bracket, it is softmax. What is this? What are these? They are cosine similarity, rather dot products. Why do we have log here? Softmax probability scores are all between 0 and 1. So see, what is our goal? My positive pairs ideally should have, what will be the softmax score corresponding to my positive pair? Softmax score will be 1. It should be 1 once the model is perfectly trained. For negative pairs, softmax score should be 0. Correct? Which means the loss, if my positive pairs are producing a softmax score of 1, what should be the penalty I induce into my model? I should not have any penalty because it's producing the perfect possible softmax score. Now, how can I convert 1 into a 0, into a loss function? I can simply take negative log. Negative simply because logarithm of any number between 0 and 1 is a negative number. So, but loss should be positive. So I just put a negative sign. So negative log of 1 is equal to 0. So I don't penalize the model at all for producing a softmax score of 1. But let's say I have a positive pair. Okay. I'm looking at a positive pair whose softmax score is equal to 0.1. Tell me, is this a good model or bad model? Why is it a bad model? Because for positive pairs, the probability softmax probability score should be as close to 1 as possible, which means should I penalize this model very heavily or not penalize very heavily? We should penalize it heavily because the softmax score is really bad softmax score. Now, if I take negative logarithm of some number, and let's say that number is a small positive number, 0.1. This will be, let's say, x. Negative log of, now let's say in another case, I have softmax score of 0.001 for positive pairs. This is model A, this is model B. Which model should get more penalty, model A or B? Okay, so now negative logarithm of 0.001 is equal to y. Which number is greater, x or y? X or y? Some people are saying x. It should be y. This is the logic. Okay, tell me log of, what is log of a raised to b? It's equal to b log a. What is log of 10 raised to minus 3? It's minus 3 log 10. What is negative log of 10 raised to minus 3? It is 3 log 10. What is negative log of 10 raised to minus 1? It is negative, it is log 10. Which one is greater, this or this? A or B? 3 log 10, 3 log 10 is greater. And what is 10 raised to minus 3? 0.001, this guy. So this y is greater than x, which means you are penalizing model B more than you are penalizing model A, as it should be. So that is why we are taking logarithm. And then we are simply, where is my formula? Then what is this 1 by n? Why do we have this 1 by n? Sigma equal to 1 to n and 1 by n. Why do we need this? Because you have multiple anchors to consider. So that the term for that is called anchor. So the image I is the anchor here. You are comparing it with other pairs to see which one is positive pair and which are negative pairs, right? So you have n number of anchors to consider. Like that, symmetrically, you will have LT to I, text to image. Just that instead of x, you will have y. X and y will be swapped. Then you take your final losses L equal to LT to I plus Li to T by 2. So this is your final clip loss. Contrastive, I mean, I don't want to call it as clip loss, but essentially that is what it is. Clip-like loss. Clip is contrastive language image pairs. That is what we have here, language image pair. Okay, now let's start coding. Please open your Google Colab. And today, in fact, we won't be coding every single line from scratch because that will take at least 3 hours. But we'll code the main parts from scratch. Main parts are image encoder, text encoder, and what else? Clip loss, those 3 parts. So I can share the code with you in 2 ways. Maybe I'll share this link with you. That might be easier. Yeah, I think you can just copy the code from this link time to time instead of a GitHub gist. Let's do that. So first is imports. We need some imports. So import math random for random number generator, then import torch for PyTorch. this is not a classification task, right? Why do we say it's a classification task? Because we don't have classes here. We have actually 243 images. Yes, if you want to call it as a classification task, it's like 243 classes, but it's not a classification task. It is, you have unique captions associated with images, and somehow you have to create embeddings corresponding to image and text that should align. And then while searching for the best possible aligning image, you can simply search based on the embedding. All right, torch, then torch.nn as nn. This we will need while constructing the classes. One more thing that we will need is torch.nn dot functional as f. So I'll tell you why this is needed. This is later needed for constructing unit vectors. After normalizing the vectors, we have to make it into unit vectors. So that's where we'll use this. This you have seen from Vision Transformer. Basically, we pass nn.module into every single class. Then import torch.utils.data. Actually, from this, we import dataset. So from torch.utils.data, import dataset. Then data loader for creating batches. Then from Python image library below, import image. This is for drawing to construct our images, image and image draw. I don't know if anything else is needed, we'll figure out. Then import matplotlib dot pyplot as PLT. For now, we just need those. If we need any more, we'll figure out. So just, I recommend you to write this along with me. That will be the best experience. But if there are parts where I copy paste the code, in those places alone, you can simply copy paste from my code. But here, I think since I'm typing, you can follow it with my speed. Okay, no module torch dot. Okay, import torch comma. Okay, next is we should have some variables that we define. So let's say variables, image size, how many pixels, let's say 32 pixel image. Then embedding dimension, let's say it is 64. And attention heads, number of attention heads, if we have multi-head attention, is 4. Then batch size 12. This we can change, of course. Then while training, we can train for like, let's say 10 epochs. Then learning rate, LR, let's say 3 times 10 to the power of minus 4 or something like this. And for clip loss, we should have temperature parameter. This we can put anything random between 0 and between 0.01 and 0.2 or something like that. So we can put any number here. If we need anything else, we can define one more thing, device equal to torch dot device CUDA if CUDA is available, otherwise CPU. This is just this we can keep it separately, but let's keep it here. So variables is done, and then synthetic data set properties. So here I have what? Colors. Then I have shapes. Then I have positions. And this, in fact, I can copy based on my other code. That way, this I don't have to spend so much time. So there are 9 colors, then 3 shapes, and 9 positions. So these are the properties of my synthetic data set. Then next is drawing image shapes. So you can access from this Google Colab notebook, right? Or is it not updating on a real-time basis? This link, is it updating on a real-time basis? If not, I can share the I can share this also, but let me know if it is updating. Okay. Okay, now let's draw the shapes. Define, draw sample. Sample is like a sample data point, and this is just a function. What we need to pass is we need to pass color, we need to pass shape. So it's not shapes or color. We are passing one color and one shape and one position at a time. And image size also we can pass. Image size, we'll pass the variable that we had defined earlier, 32. And then we say image equal to image.new of color should be RGB. Then XY dimension, I mean width and this dimension should be whatever is this image size. So I can copy paste this twice, width and height dimension. And then canvas should be white color. Then after this, we say draw equal to image draw dot draw. And then we pass this into this. And now let's see a few things. Now the way I'm drawing is like this. So I have a 32 by 32 sized image, but my canvas will be slightly smaller than that. So I will say my canvas is, I'll put a margin. Okay, so then this I will call as W, width of the canvas, and this I will call as H, which is height of the canvas. Not this, this is just the from here to here. And then I have to define a square, which looks like this, whose width is W by 2 and height is H by 2. And if my object is on the left side, I will say this is the canvas, the white color canvas in which I will draw. I mean, I will draw the object. The total canvas is of width W and height, but this square is where I'm going to be drawing my shapes. If it is at the left, if it is at the right, I'll be drawing over. This is so annoying. If it is at the right, I can draw here. If it is at the top, I will draw like here. Bottom, I'll draw here. Now for drawing, I need to define 4 coordinates. One is the top boundary along y-axis, bottom boundary along y-axis, left boundary along x-axis, right boundary along x-axis. So this is called as y0, y1, x0, x1. So for draw x0 and x1. So for drawing the shapes, I have to define these things. Now tell me if my object, okay, if my object position is top, whether it is top left or top right. For all of these 3, my y-axis will not change. My x-axis will only change, which means my y0 will be how much? What should be my y0? Actually, it's not 0. It's 0 plus margin, because I'm defining a margin also. I'm drawing slightly inside my image. Small margin is there. So basically, for all of these cases, my y0 will be margin. What about y1? It should be margin plus whatever is the size of this small square. It is h by 2. So margin plus h by 2. Then similarly, if my, let's say my object is somewhere here, okay. So my object will be drawn inside that small square. Tell me what is the x naught? What is x naught in this case? X naught will be margin plus x naught is this. It is margin plus whatever is this. This is actually w by 2. X1 is, what is x1? X1 is not width minus margin. Width is this. Width is this guy. This is image size. So x1 should be image underscore size minus margin. Or I can say it is margin plus w. I can also say that. That's also fine. And what is y naught? This. What is y naught? It should be margin plus quarter of the size of this, not half. So it should be margin plus h by 4. And y1, what is y1? Margin plus h by 4 plus h by 2, which is margin plus 3 by 4h. Right? So this, by this logic, we can define the 4 coordinates for all the possible cases. Okay. I'm not going to write all of them here because that will, I mean, all of them manually here, that will take a lot of time, but that is what we have here. So we can define a margin. So margin equal to 6 pixels, and then height equal to width equal to image underscore size minus 2 times margin, because margin is there on left and right. Margin so that the object is not going all the way till right or all the way till left. I can remove margin also, but I think that will be, drawing margin will be cleaner. That way, when I plot the images in a grid, it will not look weird because of closeness. But there is no physical reason why I cannot have a margin. Of course, I cannot have a margin also. I can keep it 0 also. And then these are now the x coordinates. So this logic is exactly what I discussed, but quickly go through it. If position is left, then x naught is margin, x1 is margin plus width by 2. Now it doesn't matter. So this is only for x coordinates. For y coordinates, I have a separate. But then look at all these three. For all of these, it doesn't matter whether something is top left or bottom left or left. For all of them, x coordinates does not change. Y coordinate only changes. So see, this is x naught plus margin, x naught equal to margin, x1 equal to this. Same for this and same for this. Because x coordinate is independent of whether something is top or bottom or center. And same here, as long as something is right, it doesn't matter whether it is right or top right or bottom right, there x naught and x1 will be the same. And then for center, okay, let's discuss only that case. What if my object is at the center? What should be x naught? X naught should be margin plus 1/4 of the width, margin plus w by 4. This will be margin plus w by 4 plus w by 2, which is margin plus 3w by 4. Same for height. Height will be margin plus height by 4. And this will be margin plus height by 4 plus height by 2, which is margin plus 3 height by 4. So that is this guy, x coordinate. Now y coordinate also has same logic. So it doesn't matter for y coordinate whether something is left or right or center. As long as it is top, its y coordinate y0 and y1 will be similar. Y0 and y1 are these two, y0 and y1 are these two. This is also the same. Same logic. As long as something is at the bottom, it doesn't matter whether it's at the bottom or bottom left or bottom right. It's just the bottom. So y coordinate is not affected. And then center coordinate. So this is the logic. So I'm going to just copy paste this part so that we can save some time. Once I write this, I will share the code with you. And then we can simply say, if shape equal to square, draw dot rectangle. So rectangle is the most general form of square. And then we pass these four. Fill equal to whatever is the color. And where is this color coming from? We are passing the color over here. Then passing the shape here, passing the position here. So color equal to that, outline is black. If shape is circle, again we define the limits, but then circle will be drawn inside that. Fill is whatever is the color, outline is black. For triangle, there is an exception. You need coordinates of, you're mentioning coordinates of 3 points rather than the bounds. So first point for triangle, it will be like this. If you are drawing a triangle inside this, 1 point will be x0, y1. This will be x0, x1, y1. And this will be x0 plus x1 by 2, y0. These are the 3 points you have to pass. And that is what we are passing here. Draw dot polygon of, actually this x0 plus x1 minus x0 is same as, if I just delete this and keep this as plus, the same thing. So this is how we can draw these polygons. So I'll paste it here and that's it. Then you return the image. So return the image means that image that is created, which was defined here, will be created. So I'm just going to share the code with you. Maybe I can share here. So you can find the code from this GitHub gist. All right. Now let's just run this. Nothing will happen because we are not yet, calling the function. We just defined it. Then we need, so this is just the image draw function, but we have to call it in a little bit loop fashion, right? Because we have 9 shapes, 3 shapes, 9 colors, 9 positions. So let's write the code for calling the function multiple times. Class for calling class for building our data set. So then we say class shapes dataset. The first item will be the init constructor, define underscore init bracket. And to this, we are passing the self, which is the current object that we are looking at. Self is the current object's reference. Then we say self.images. So we construct an empty array for appending images one by one. We construct an empty array for appending captions one by one. So that each time when we construct an image by calling this function, and when you get the image returned, you save the image here. Self.images and self.captions. And then we say for C in colors, you loop through all of that. Then for P or S in shapes, you loop through all the shapes. And for P in positions, you loop through all the positions. Then we say image, which you are getting from this function, what was the name, draw sample or something. So now you have to call the function here. Image equal to draw sample, but here we pass C, S, P. Image size you don't have to pass because it's already, there is a default value there. And caption equal to, for constructing caption, we need a dynamic variable. So this will be 3 things, right? First is whatever is the color, second is whatever is the shape, third is whatever is the position. So now this will be like a dynamic string. You are saving the caption as a string. And then you say, okay, now once these things are, actually you have to append also. So then you say self dot images dot append. And here you have to convert the image into a torch compatible format. So what you can do is, you can just, let me just take this code alone so that I can save some time. So here essentially what, okay, numpy, load numpy as empty. So just have that also, because here numpy is not getting recognized. So now we are creating the image and we are appending it here. And what we are doing is permute 201 is it will convert it into R, G, B format, and values will be between dot float by 255 values will become between 0 and 1. Self dot captions dot append dot cap is to that array you are appending your each floating point caption, not floating point, a string caption one by one. Then you go out of the loop and then you say self. Okay, now you have to have a vocabulary builder. So first let's write that. So define build vocab, because you have 22 unique items to be defined inside the vocab. I don't know why there is an error here, maybe because I'm not define init. Yeah. Define build vocab and words. I need words and I need to add those words to vocab. And I need the words to be converted to indices. Yeah, I know that I'm missing two things here. I will add that. So self, and one more thing is we need to add, which is the text that we are passing here. So let's say text, and we need to convert words to indices. So words to index equal to, we need that. And then we can return two things. One is we can return vocabulary itself and word to index. You'll see what this word to index will do. Now, what are the words? The words are, first we need to do this for actually there is a short form that I had written here. I will show you what the short form is doing. So can you tell me what is happening here? This is one line, but bunch of things are going here. What's happening here? So first is we have the incoming text. So for T in text, we are doing T dot split. So T in text means you have bunch of captions and you are picking it one caption at a time. So this is 2 for loop, one inside the other. So you first loop through all the possible captions. You have 243 unique captions. So T in text means each T will be one caption. But then T dot split means you will split the caption into the 3 words. 3 words are color, shape, and position. So now W is nothing but those individual words. So now what is being stored in a sorted array is the word W, and only unique items will be stored here. So here we can print these words. I'll show you what these words look like. So words is basically, actually, you know what? I can just let me comment this for a moment and I'll show you what this looks like. Data set equal to shapes data set. And then I can say not yet. I need data loader, but let's continue here. Words equal to sorted. So these are now the sorted unique words in alphabetical order. And then I will say vocabulary is nothing but words plus one more thing. Yeah. So this is for defining a set, correct? So you are appending to a set whenever there is a unique item coming. Now words, you are adding one more item to the words, which is CLS token. So then you say words plus CLS. Actually, CLS should be like this, because this is the CLS token. You are putting it in quotes, and then you are putting it in a bracket because you are adding it to your words. And then word to indexes, you can create another set. Actually, let me copy that from here. For every word, you are creating a word to index pair. So for every word I, W, you are basically enumerating your vocabulary. So whatever is the item number 0 will be CLS. Actually, you know what? This should not good. I should put here. I want CLS to come at the beginning. So CLS should have the index number 0. Then remaining items will be alphabetically. So A should be, I don't know if we have any color or something starting with A. A or B. B is there, blue is there. I, J, K, L, M, N, O. So maybe I think the after CLS, perhaps this might be the next token. Blue might be the next token. We'll see. We can print it and see that. Okay, then we have to call this vocabulary builder somewhere. So we say self.vocab, comma self.word to index. Word to index equal to self dot this function of, and then to this we are passing all the captions. So all the captions are in this self.captions. So that is the vocabulary builder. And then we need something that can encode the text. So define encode text and pass self here. And here we are passing one text at a time. So define encode text of self comma text. And then we need to create tokens. So tokens equal to, so I need one token for CLS and one token for all the words in my input. So let's check the code. So one token for CLS, then one token for all the words in my input. So whatever incoming word is or incoming caption is, that will be split into tokens, and those tokens will be part of this talks tokens, and then CLS will also be part of that. And then I can just return tokens. But it should be like a tensor format. So return torch.tensor. And then I think that's all. We don't need anything else. Define get item. Yeah, we can. If you want to print one image to see how the image looks like, define get item self comma idx return, and then this should return image and the encoded text. And I think that's it. If we need anything else, we'll add on the go. So this will hopefully build the shapes data set. Let me share this in GitHub gist. I'm adding it at the bottom, so please don't, I'm leaving a space between, so just take it from here. So this is that class. Okay, now I think we are ready to create the full data set. All right. Full data set is equal to, it should be an object corresponding to this class. And then I need a variable for storing what my vocabulary size is. So vocab size is equal to full ds dot, what was the variable? Vocab dot vocab, and I need the length of that, len of that. And if I want to see the vocabulary size, I can just print it. And hopefully this should print as 22. If it is not 22, something should be wrong in the code. So that will be a sanity check. Okay, something is missing. Shapes dataset has no attribute called bill vocab. Indentation, yeah, defining it. Yeah, I think so. Yeah, thanks for that. Yeah, it was, I had an extra indentation to the right, so I just put it to the left. So vocab is fine, vocab size. Let's print the vocabulary also. I should then see if I print this full vocabulary. First word should be CLS, second should be blue, if I'm not wrong. Yeah, first second is blue, bottom. So this is like an alphabetically ordered vocabulary. So in my vocabulary, there are 22 tokens. Okay, so that is good. So now we are good to move on. So our data set creation is done, but we can print some data set. But before printing, let's create training and validation data. So train val data creation. So train size should be equal to whatever is the length of my data set. So whatever is the len of full DS, well, let's say 80% of it. And then val size should be 20% of this. Or let's say len of full DS minus train size. And now we can create the random split. So train DS comma val DS equal to random torch dot utils dot data dot random split. And here we pass the full DS and then mention the train size and val size. I think that's it. Shapes dataset has no len. I need the length of the full data set. And where is that? Images, maybe. Or not vocab. Vocab is 22. I need the length of maybe captions or something. So shape full dot captions, perhaps that should be 243. What shapes data set has? Oh, full DS. I am not sure what's going on. Let me print this. Okay, length is 243. And if I try to do this 0.8 times, and I need an integer, not a float. So if I do this, it should work, right? Val size. What's the issue with val size? Okay. Okay, got it. So it should be about this? Int of len we should define in the class. That is a good suggestion. I think I had it earlier. I think I had it here. Yeah. I think that was the issue. I should return self. Yeah, sure. That's a good suggestion, whoever suggested. Thank you. So now hopefully it should work. But here I don't need dot captions. I just need len of full DS. Now what might be the issue? Yeah, I'm already taking length, which means but how about this? If I just print, so this seems to be perfectly working. Len of full DS. This seems to be perfectly working. And I can assign it to something. And b equal to this minus int of this. So b equal to len of this minus a. And if I now print a comma b, I should get something, right? Okay, it seems to be, this seems to be perfectly working. I am not sure what exactly, if I copy this. Len of full DS minus train size. I have no idea what is the issue here. Let's ask Gemini. No, it should not be length of vocabulary, right? Because vocabulary is fixed irrespective of whether I have 300 images in my data or 200 or whatever. Vocabulary is 22. So we should not take vocabulary. We should take rather, okay, now it's working. What's the difference? Let me just check. Object of int has no length. What did change right now? I'm not sure what changed, guys, but whatever. I don't want to spend time here. I would rather spend time in the coding part of the encoder. But anyways, now let's pick data loader. So train loader and val loader. So here is where we define the batches. So data loader, this we had done in the last lecture also when we coded transformer. So here we pass train DS and here we pass val DS, validation data set. But then we have to say whether what should be the batch size. So batch underscore size is equal to batch size and shuffle equal to true for training, and shuffle, we don't want to shuffle for validation. It's not needed. So this is now the data loader. Okay, so far so good. And I can just now show you a random sample. So this one I don't necessarily want to write. Display sample data point. now let's see if our images are working. Not enough values to unpack. Let's run everything to see if images, comma, captions. Okay, so 243 images are split like this. Not enough to unpack. Okay, let's ask Gemini, which will give us the fastest answer. Okay, so blue circle to the left, it is fine, correct. Brown circle top left is correct. So these are, now we are displaying random images just for sanity check. Yellow square top, gray triangle bottom right. So seems like most of the image types are getting created. Orange triangle bottom right. So everything seems to be correct. I will do one thing. I don't know till where I share the code. I will share the display code with you. Train size much greater than full DS in trains split line. Okay, that was earlier. Okay, but this you guys can also run. I hope the rest of the things you got. Train loader, this part is fine. I don't think rest of the things are fine. Okay, so our data set is good. It's working. So now what should we do? We are ready to now write the encoder. So first, let us go about image encoder. And then after this, we will write text encoder. And then after that, we will write click loss. And then we will do training. And then we will check validation. That's it, right? Okay, so now start the fun part. So define, or rather class image encoder. And here we pass nn.module. And then define then init constructor self. Let's delete this. I will add this later. The super constructor, super is calling the init constructor from the nn.module. So basically parent class is different. We are inheriting bunch of properties. So this will call the init constructor of the parent class. Now we'll decide what all things to pass here. But before that, what was our architecture like? We had 4 convolution operations, right? And then following that, we had max global average pooling, then we had projection. So let's write it. So self dot convolutions equal to nn dot sequential. Why? Because we are adding operation sequentially. Then first is nn dot con 2d. And here we have to mention total number of channels for the first convolution layer was 3. Output number of channels was 32, so we need 32 filters. Kernel size was 3. Stride was 2. Padding was 1. Then following this, we have another one where input is 32, output is 64. Remaining are the same. Then here input is 64, output is 128. Remaining are the same. And then input is 128 and output is 256. Now, one crucial thing that is missing here is, can anyone mention, there is one important thing that I'm missing here. The important thing is activation. So let's add ReLU. All right. Then that's it. For convolutions, that's it. Then we need, after convolutions, there is a global average pooling, but for that, we don't have to define a function. We can just operate it on the go for all the inputs. Yes, we can check without activation also. Then we need a projection. Self.projection equal to nn.linear. So it will be a linear projection from 256 to whatever is the embed dimension, which means I have to pass the embedding dimension somewhere here. Embed underscore dim equal to embed dim. So embedding dimension we pass, and then self dot normalization we need layer norm, or just norm, layer norm 1 equal to nn dot layer norm of, and these many, along these many dimensions we are defining the parameters. Now that those are the functions, but now we have to define the forward pass. So define forward self comma x, and here we do the actual implementation of the convolution. So we say x equal to self dot convolutions of x, then x equal to, we have one more thing to do, but I'll do that after adding the projection. So self equal to x dot projection, self of projections of x. Yeah, indentation. Thank you. Then x equal to, so here we use this guy. We had defined a torch dot nn functional as f. So here we say for converting this into a unit vector. So x equal to f dot or f of dot normalize of self dot norm of x. Self dot norm of x was, or layer norm 1 of x, comma along column dimension. So along dimension or last dimension equal to -1. Then return x. But here I'm missing again one thing, important thing which we discussed, which is gap, global average pooling. And that we have to implement before we project into our embed dimension, because in our diagram, global average pooling was, the projection happens here, global average pooling happens before projection. So it has to, we have to write it here. So then what we need to do is x equal to x dot mean of, so first dimension is channel dimension, second dimension is x dimension, third dimension is width dimension, height and width dimension. So we take a mean of along dim equal to 2 comma or 1 comma no 0 1. I'm not sure if it is 1 comma 2 or 2 comma 3. Let's try both. We'll first try 2 comma 3. If this is the issue, it will be 1 comma 2. But basically, I need to preserve channel dimension. I want to do average along the individual channels for all the individual channels. Okay, I think that's pretty much it. I don't think I'm missing anything. If we are missing, we'll figure out. So first is the channel dimension. So I don't think 0 should be there. My only doubt is should it be 1 comma 2, or because there is a batch dimension also. Yeah. So yes, first dimension is batch, second is channel. So 2 3. So it should be 2 3. So I think this is correct. Next we can write text encoder. So class text encoder of nn.module. So this should inherit properties from nn.module. And then we say define then init constructor underscore init underscore self, then super underscore in dot underscore init nn dot sequential spelling. Okay, yes, sequential. Yeah, thank you. Okay, actually, let me run this to see if there is any other issue. Okay, yeah, now it's working. Init, then, so first we need token embedding. So self dot token embedding. Then I need self dot position embedding. this is equal to something, this is equal to something else. Then after position embedding, we need multi-layer perceptron. So self dot or multi-head attention, not multi-layer perceptron, MHA. And then after this, we need layer normalization. So self dot norm. Then what else? I think that's it. Among this, the easiest one is MHA. So this will be NN dot multi head attention of, and multi-head attention for this we need the embed dimension. And what? One more thing. What else do we need in multi-head attention? Attention heads. So maybe I can call it as num heads. And then this we have to pass. So embed dim equal to embed underscore dim. And num heads equal to, if I remember correctly, I called it as attention heads underscore heads. Okay, and self dot token embedding should be nn dot embedding. And what should I pass here? I need to pass two things. So this is slightly different. So here we are creating token embedding for every single item in the vocabulary, not just for the context window. For this one particular line. For position embedding, it's for the context window. So here we need the vocabulary size underscore size. So this is a crucial difference. Vocab underscore size, comma, each item in the vocabulary is that of embed dimension. Embed underscore dim, which means I have to pass vocab size somewhere. Size is equal to vocab underscore size. Okay, so that is done. Then position embedding, again, also this should be nn dot embedding. But what should this be? What two things should I pass to position embedding? One is obviously embed dimension. Another is the context window. Context underscore window. What is the context window size? It is not 3, it is 4. Because CLS is also there. So context window is equal to 4. Okay, so that we pass. Then self dot norm is simple. NN dot layer norm along embedding dimension. So those are the functions. Then we can define forward pass. So define forward pass. Into that we pass self. And earlier we used tokes for tokens. So we can consistently follow that here, although it's not needed. Now let's see what all things we need. We first have to create token embedding, and then we have to add position embedding. So first let's do this. Can you tell me what will this be? What will be the value of this? Shape will be like what all things will be there in tokes dot shape. So this is the text encoder, right? So one dimension has to be the embedding. So let's go back to our notebook. See, one dimension has to be what is that? The embedding. Another dimension should be the sequence. So let's actually write it in this way itself. N comma L is equal to talks.shape, tokens.shape. And then one thing we have to do is in the last lecture, if you remember in vision transformer, we had expanded the position embedding in a certain way so that we have that many number of position embeddings. So in position embeddings, what we want is by default, what we will have is something like this. If let's say L equal to 4 and N equal to 2, what this means is you have two sequences of length 4. Length 4 because you have CLS token followed by 3 other tokens, and you have two such sequences in the current batch. So ideally, you want something like 0, 1, 2, 3 repeated 2 times, because position embedding should not change. Position embedding is position number 0, position number 1, number 2, number 3. Same for the next batch. So what we use is a code that looks like this. So first we create a range of numbers. So a range is a range of numbers whose maximum length is L. And L we will get from the shape of the tokens. So L is the total number of sequence items in the sequence, which is 4. And into that we pass the device. The reason why this device is passed is in case we were running on GPU and we did not pass anything for the device, by default this range of numbers are created using CPU. But if our tokenization before was done in GPU, then that will cause a conflict. So it's better to pass whatever was the device as device equal to tox.device. Then third thing is unsqueeze of 0. What unsqueeze of 0 does is it creates an extra dimension. It adds one more dimension based for the batch, and then expand n comma L means it will add. So if batch size is 3, it will expand it multiple times. So same thing will be repeated n number of times. I'll just use the code as such. So x equal to or position embedding equal to torch.arange of L comma device equal to tox.device, whatever device was used while creating the tokens, and dot unsqueeze of 0 to create an extra dimension, the 0th dimension, and then dot expand n comma L. And then we need position embedding to be added somewhere. Plus now to create tokens, okay, let me explain one more line. Self. So now this token, can you tell me what this tokens will contain? What this tox will contain? Let's say I have a batch size of 2. Size equal to 2 and sequence length L equal to 4. And what will this tox contain? It will have, of course, sequence of tokens, but the question is what that sequence will look like. Will it be the vectors or will it be something else? It will be the IDs of those vectors. It will not be the actual vectors themselves. So these numbers will be simply integers, 0, 17. It will go from 0 till maximum will be 21 because the dictionaries, the vocabulary size is max 22. So it will go from maximum 21 will be the index. Now from this, we have to get vectors corresponding to these IDs, right? So for that is why we had defined earlier this nn.embedding. So from the vocabulary, a particular ID item will be converted into a vector of the embedding dimension. So what we can do is we can pass tokens into this self.token underscore embedding. So pass tokens here. And then we say token underscore m equal to this. And then you can actually add position embedding on top of this. So now you have not yet, but position embedding, this is just position embedding ID, but you should pass that to this. because position embedding also should be vectors of dimension 64. Currently, this will simply be 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, but that has to be converted into position embedding vectors. So you pass it through here. So an easier or simpler way to write that is position embedding. This is position embedding ID. Then position underscore embedding underscore vectors is equal to self dot position embedding of this. Then token embedding vectors is equal to, or to make it even clearer, token embedding underscore IDs is equal to tokens. But to convert this IDs, token underscore embedding underscore vectors is equal to, you pass the ID to create the vector. Then final embedding is equal to token embedding vectors plus position embedding vectors. So now this is the final embedding, and this final embedding goes through multi-head attention. So then we say final embedding equal to self.mha of, and we have to pass this 3 times. This we had discussed last time. Oh, argument is there any mistake? I think, yeah, position embedding IDs. We should pass position embedding IDs here. Thank you. So final embedding will be, you have to pass this 3 times. The reason why you have to pass this 3 times is because query key value has to be created from input. So it's not always from the same input as you saw from the visual Wilbert paper. Sometimes query and key can come from elsewhere. So that's why you pass it 3 times. And the output that you are looking at is at the 0th index. So 0. And then you have to do normalization. But before that, we have to do one thing. What is that? Now we have the context vectors. This is actually, let me not call it as final embedding. Let me call it as context vectors. That will be better. Now what should I do? Which one am I going to use? Which context vector? I'm going to use CLS tokens context vector. So that will be final underscore token equal to context vectors of 0th item. So this is the batch dimension. This is the 0th item in the sequence. Now what we have to do is we have to do a layer normalization. But before that, usually in vision language, vision transformer, you might remember there was a classification head which was projecting it into the final dimension required, which was projecting the context vector into the final dimension required. So if you look at this image, this MLP head was the classification head. So we can add one like that just to be consistent with how other models are. So projection is equal to final token of yes, we should transform to unit vectors also. So we should pass the final token into a projection. That projection we have not defined yet. So self dot projection of some input dimension. Let's write what this is to output dimension. Output dimension should be the embedding dimension. And here input dimension also happen to be embedding dimension simply because our multi-head attention is not changing the dimensionality from input to output. So this just happened to be embed dimension. Final dimension should be anyway embedding dimension because we want to compare this with image. But here input dimension to the projection layer just happened to be embedding dimension. That's all. It's not always, need not always be the case. So then we pass to the projection layer. So what do we pass to the projection layer? The final token. And then after this, we do the normalization. So then we say output equal to f dot normalize of, self dot projection should be nn dot linear, my bad. Yeah. output dot normalize of self dot norm of projection, comma, dimension equal to -1. We have to do it along the column. So that's it. I think we are good to go. The problem is we are using too many variables. Now that you know what these variables are for, we can simply do the following. X equal to, let me delete this. So I'm just going to simplify. Now that you know what all of these things are, just this tokens I will use here. Then I'll remove this. Now you know these are the context embedding vectors. Then final embedding I'll call as X. X is equal to token embedding plus position embedding. Then I'll pass X here, X comma X comma X. That is equal to X. And then final token also I will call as X equal to X of 0. Then projection equal to X equal to this of X. Then output X equal to of X. So this way it's a bit clean. And then return X. So that's it. That's it for the text encoder. I hope it should run. Okay, it is running. Then the last thing, it is we'll look at the text encoder without attention, but currently it is with attention mechanism. Next is last thing, clip loss. Now clip loss is just a function, clip underscore loss of, and here we need to pass image embedding, text embedding. So this code I will share in the GitHub gist. Or I guess you can just refresh also, should be fine. And then temperature. Then first we need logits, and then logits can be used against targets to construct the cross entropy loss. And there is loss from images, then loss from text. Then what we can return finally will be average of these two. I plus loss due to text by 2. Now let's say logits is equal to basically the dot product. So image embedding multiplied by text embedding dot t divided by temperature. Then, okay, now let's see. X equal to, so this is, you are taking the only the CLS token, which is the token number 0. First index is corresponding to batch, but for every batch among the sequence of 4 items, we are taking the 0th item. So that's why X equal to X of colon comma 0. Just to extract the CLS token, so that token's representation we will use as the final embedding, final text embedding. And that text embedding will be compared here against the image embedding. Okay, so now targets should be what? Can you tell me what the target should look like? What I mean by target is, let's say I have a batch of 12 images. For first image, which caption is the ground truth? For image number 1, caption number dash is the ground truth. Caption number 1. For image number 10, caption number 10 is the ground truth. So targets will be basically 0, 1, 2, 3, etc. up to 10. So for image number 1, targets will be first item, target will be first item in the targets array. For image number 2, the target will be of the index second item in the targets array. So basically, and this is because my image and caption pair, I don't need to know what is the caption. I just need to know the index of the caption in my targets. So this is how we will align. So targets will be torch dot a range of And here, whatever is the number of images, so image embedding dot size of 0, that many range of numbers I need. And then here also we have to pass the device. So device equal to image embedding dot device. So that whenever we create this torch.arrange, PyTorch by default Python creates it in using CPU. So if we are using GPU for rest of the computations, if we don't pass this, it will cause a conflict. Then loss is simply f dot f we had defined earlier by doing the imports cross underscore entropy, and here we compare logics against targets. Now you might have one question: where is softmax applied here? Softmax is implicit; it's inside the function. So here we are not having softmax. Okay, we are passing logics and targets. Softmax is part of cross entropy loss in Python. Now one more question. Now for loss with respect to text, what should I pass here? So let's say I'm taking text number 3, right? What should be the what should be the ID of the corresponding image target? If I'm taking text number 3, it should be same as 3. So targets need not change. The target array can still stay as exactly what it is. So this can remain as it is. But instead of passing now the logics, I have to pass the transpose of the logics. Why? Because just go here. Look at the clip loss image. Where is the image? So in one case, you are comparing all these items. In another case, you are comparing all these items. So the logics corresponding to your image are found in the column. The logics corresponding to, text are found in the column. Logics corresponding to image are found in the row. So if you want to access the ones in the column, you can simply access it by taking transpose. So we can send pass logics.t here. And I think that's pretty much it. Nothing else. Okay, so now we have defined most of the things. Now only remaining thing is the model, then data optimizer. This we can define vocab size we already have. So image encoder equal to image encoder dot to device. Then text enc equal to text encoder dot to device. And parameters that we are going to now optimize during our training will be whatever parameters are there in both of these encoders. So I can just say list image encoder dot parameters plus list of text encoder dot parameters. And those are the params that we are optimizing. Then optimizer equal to torch dot optim dot. Then these parameters we are optimizing, and learning rate equal to, we had defined it earlier as LR, I think. Yeah, LR. Target need not be .t. So that's what I'm saying. See, targets should be simply those numbers 0, 1, 2, 3. Image number 1 correspond to text number 1. Just like that, text number 1 corresponds to image number 1. So targets, we can just pass the same targets. Okay, so this much. Okay, so now it's working. Now we can simply run the training. So now we don't need to write the training part of the code. It's anyway for all models the same. Let us do one thing. Let's display some embeddings before training so that you'll see how the embeddings look like. Some random embeddings. text in case not defined. Let's run it here itself so that variables are matching. Yeah. So I'll share this full code with you. I think here I have defined some other variables compared to what this function is. But just look at this. What we have is we have this image and this caption. So this is orange triangle top. And look at the embeddings before training. Before training, embeddings look completely different. There is very little, if you compare it dimension to dimension, there is very little similarity. Very few dimensions are exactly matching. And then I have a training loop. So this part I'm not interested in writing. It's just training through different batches and printing the accuracy. And you can see validation loss is decreasing continuously. And let's see the embeddings after training. Look at this after training. It's very, very, I mean, I'm not saying exactly similar, but it's much more similar than earlier. And then the dot product, the similarity looks like this: minus 0.51 before training and 0.9197 after training. We can do one thing, keep number of dimensions to be just 3 instead of 32. And let's look at how the embedding looks before and after training. Oh, embedding dimension should be divisible by number of attention heads for sure. So attention heads, let's keep it 3. So now text encoder, yeah. So now this is how the image looks like before training. Slight difference is there. Yeah, temperature, of course. So yeah, very important. Temperature value will definitely make the dot product loss different. Lower the temperature, higher the penalty for making mistake. See, here I have plotted it into, so this loss, look at this. These are negative pair, positive pair. Now, if I want to penalize the same negative pair more, all I need to do is reduce the temperature, 0.001. Oh, 0.01, let's keep it. Yeah, see, now when I kept it 0.01 for the same mistake, the similarity score has not changed. For the same mistake the model made, we are penalizing the negative models more and positive model less. So this is the 0.01 temperature, but if it is 0.2, it will not get penalized that much. So I'll do one thing. I'll directly share this with you so that you can just run it yourself. Yeah, just take this code. This is full code. Now after, so this is before training, and if you run this once more, it will pick a random other example. See, this is completely different, right? So this is a very different. If I plot this in 3D, actually we can do that. Ask Gemini to create a 3D plot of these vectors. Create a 3D plot of these 3-dimensional vectors as arrows before training. And let's run this to see how the 3D plot looks like. So this is how the 3D plots look like between image and text embedding. This is before training. There is, of course, cosine dissimilarity between them. And after training, the same 3D embedding. So you see why the validation loss is not decreasing so much. It's because the expressive power is less. It's a 3-dimensional embedding. In 3-dimension, you are expecting to capture all the information in your image and your caption. It's not easy, right? That's the reason why validation loss is not at all decreasing very much. But final embedding is actually very bad. Let's run once more. Okay, post training, this is how it looks like. Cosine similarity before training is 0.52, after training is 0.96. And the 3D plot before looks like this. 3D plot after, we can plot one here. Create a 3D plot like this for after training. Yeah, so this is after training. See, much closer. Those two embeddings in the same 3D space are now much closer than before. So this plot actually tells a lot of story, right? It's very it's simple to see, but it's very good. Let's come back to 64 dimension. I want to show you one last thing before we wind up. So embedding dimension, let's keep it at 64. The last thing I want to show is the image fetching for a given. Oh yeah, so this error is because for the 3D plot, I should not provide more than 3 embeddings. So I should just comment, it works only if the number of embeddings are 3. Otherwise, maybe we'll have to take 3 principal components or something like that. And attention heads, yes, thank you so much. Attention head should be 4 or something divisible, something that divides 64 perfectly. Last thing which I want to show you is this. So this is the image. Brown triangle center is completely wrong. Green. Okay, there is huge mistake here. Green triangle bottom right. Actually, the model is not at all good. Let's see what is happening. Green circle top. I know what might be happening. I think I have messed up something in the code because embedding is not coming out correctly, but this is easily fixable. Comment 4D text, 4D text encoding. Where is that? Yeah. I think this is because this is a text encoder class without attention. Yeah, we added 4 convolution 2D. This is correct. This part is fine. No issue. But I think somewhere, let me just restart the session and activation is there. So ReLU, nn.ReLU is there. But what is missing is something else. I initially thought batch first equal to true, that was missing, but that's not the case. It is added here. Actually, here I did not add that. I was about to ask you to add that later once our error is so high. Here, you remember from our last lecture, we had not in position embedding in multi-head attention. Here we had a batch first because the first dimension that MHA should consider should be batch first. But anyways, let's see now what happened. after training. Okay, so clearly something is missing here. Okay, training loop is committed. Of course, that's why. Yeah, now it should be fine. Okay, this is post-training embedding. Looks like they are similar. Yes, after training, there is very good cosine similarity. And yeah, I just want to show this retrieval. That was my only purpose of running this. Orange circle. So now this is the first task. First task is for a given image, what is the perfect caption? Perfect caption, orange circle left. We know that this is orange circle left. So it is indeed the perfect caption. This is for this caption, which one is the best image. For orange circle top right caption, this is the best image. And if each time we run this, it picks a random image and it shows I don't know why both of them are square. I don't know why the shape remains the same. When I ran, yeah, see now it's different. See, image 18 best caption. So image 18, this image is, we know it's brown square left, and indeed that caption is picked up. And this is purple triangle top right is the input caption. Corresponding to that, the best image is this. So clearly our model is working very, very well. Yeah, so if in the code which I shared with you, in case if I accidentally mask the training loop, please unmask it. I mean, this was accidentally commented out, but you see the validation score is coming down. I just want to run the 3D thing once more, just to ensure that for 3D also I can recover or not recover. So 3 dimensions and attention head is equal to 3. Let's see how bad is our fetching at the last. So validation loss is decreasing. And post-training, see the embeddings look very similar. Pre-training embeddings were looking like this, completely dissimilar for the 3 dimension. And when we are fetching the image, purple square right, yeah, there is mistake because this is 3D. In 3D embeddings, we can capture only so much information. We can't capture everything. We are expecting this three numbers to capture everything that is there in this image, this text and in this image, which is impossible. So clearly it's making mistake. But you can see by increasing the number of dimensions to even 12, I think this will work. You don't need 64. So see, now with just 12 dimensions, your validation is much better. These are now the 12 dimensions after alignment. And then at the end, gray square top, and this is gray square top, blue square right, blue square right. So you can play with this to see for just bare minimum dimension whether it works or not. Now let's do one last thing. We are about to wind up. One last thing. Why did we call this as a NanoVLM, right? So let's do a quick calculation about how many exact number of parameters are there. So image encoder had input as 32 by 32 by 3. It was 32 pixels by 32 pixels multiplied by 3 channels. And it was getting converted to 16 by 16 with 32 channels, which means I have a 3 by 3 kernel with 3 input channels and 32 output channels, then plus 32, right? So let me bring my calculator to see what this number is. So 3 times 3 times 3 times 32 equal to 864 plus 32 will be 896. So this has 896 parameters. Then the next one will be 32 channels at the input, 64 at the output, 3 by 3 filter plus the bias. Then this will be 32 times 3 times 3 times 64 plus 64 equal to 18496. Please do the calculation along with me. I hope I am not making mistake. 32 times, oh, is it? Okay, let me do once more. 32 times 3 times 3 times 64 equal to this 18432 plus 64. It's correct, right? Okay, I hope it's correct. If I'm making a mistake, we'll see at the end. Then next one is 64 in the input, 128 at the output, 3x3 filter plus 128 bias. So 64 times 3 times 3 times 128 plus 128, which is 73,856. Then next item is 128 at the input, 256 at the output, 3x3 filter. So 128 multiplied by 3 multiplied by 3 multiplied by 256 equal to this. Oh no. 128 times 9 times 256 equal to, then with this we add 256. See, now the later layers are contributing so much. So 295,000, 295, 168, 168 or 169, I forgot, 168, whatever. Then global average cooling has 0, doesn't contribute anything. Then this is the embedding 256 projection, 256 times 64 plus 64, which is 16448. And then last is 128. This is the normalization layer norm. So if you add all of this, you will get a number like this: 400,000, 4,000, 404,992, basically around 400K parameters. So around slightly less than 500,000. Then in text encoder, let's think about the parameters. I have vocabulary embedding. So I had an nn.embedding, which was 22 by 64. So this is 1408. Then I had position embedding. So I required for 4 positions, I need 64 dimensional vector. So this is 256. Then in multi-head attention, I have, let's say, 4 attention heads. We also had a linear projection layer in the code. So which linear projection in the convolution neural network? So linear or in multi-head attention. In CNN, this is itself is the linear projection. 256 times 64 plus 64. Now in text encoder, in MHA, we have weight matrix for query, weight for key, weight for value. So if I have 64 dimensional embedding and 4 heads, each in query space, key space, and value space, dimensionality will be 16, which means the WQ matrix will be 64 by 16, WK will be 64 by 16, WV will also be the same, and it will have bias. So 64 by 16 plus 16 for the bias, and I have query, key, and value. That's why I have this 3, and I have 4 attention heads. That's why I have 12480. But there is one more thing. At the output of multi-head attention, we are concatenating. And to mix those concatenated 64 dimensional embeddings, we have an output projection layer, which is part of the multi-head attention. So that projection will convert numbers from 64 dimensional concatenated outputs to 64 dimensional mixed outputs, so that it's not just 4 multi-head attention values simply concatenated, proper mixing is happening. So this happens through a 64 by 64 matrix with 64 bias numbers, bias values. So that will be 64 times 64 plus 64, which is 4160. And then you have a projection. The projection was the classification head like mode. Where is that? This one, this projection. So self dot projection was an nn dot linear from embedding dimension to embedding dimension. So that will also contribute 64 by 64 plus 64, because projection, the input dimension just happened to be 64, output has to be 64, and bias will also be 64. So this will also be 4160. Final layer normalization is you have 64 dimensions, beta and gamma for each dimension. So 128. If you add all of that, you will simply get 22,592. So total number of parameters is 4,992 plus 22,592. So this is what, roughly 4.26 or 426K or 0.426 million parameters. Let's call it as 0.45 million parameter for a rough figure. So this is why it's nano. Typically, models with less than 1 million parameters we can call as nano. So this is the reason why we are calling this as a nano vision language model. So I hope this is a good time to stop the lecture. The lecture has gone 1 hour extra than I expected, but I kind of expected in the back of my mind that it will go beyond time, but I hope it was worth your time and you enjoyed it. Please try coding once, at least the 3 parts yourself, the text encoder, image encoder, and clip loss. Other parts are okay. Other parts you can use my code directly, but just try with these 3 things. I think you will learn a lot from that process. Updated collab link I will share once in the chat. 1 second. Also, just play with the dimensions because for 3 dimensions, it's clearly not working. For 12 dimensions, it's working very nicely. Maybe for 6 dimensions also, it may work. The thing is, lower dimensions means you can plot and get a lot of meaningful insights from it. So just try this out. I hope you have enjoyed the lecture. You please read the papers. You can start with, even if you skip the bird paper, I think it's fine. But at least read the visual bird paper and will bird. Those 2 papers might be really good for you. Few number of pages, and then I don't think it'll cause you a lot of mental struggle. I think it'll be fine. So thank you so much, everyone. We'll meet again next week. Hope you learned a lot, and hope you're enjoying the series. See you soon. Bye.